from his presentations. So, in fact, it's very much a subset of his presentation because he goes quite a lot further, and I'm leaving out a lot of the more complicated mathematics, and just in order to appeal to a wider audience. If you are interested, obviously, his papers and books are easy to find, and I'll put some links in the chat as well after that. So we've actually also, I think Tim has already asked Larry to appear on APEC, but he doesn't want to. So I'm hoping to do his work justice. Obviously, I'm sure if he wants to appear after this and and correct me or anything else, I'm sure Tim would welcome his appearance. So, right, I'll just move on. Okay. Yeah, so just to, it's kind of a resume of, and then to relate this back to Jennison's work, we start from a signal generator, normal traveling wave, which you can imagine you could then trap inside a resonator of some kind of hollow tube or cube of some kind. And when it's at rest, you just have a standing wave because it's just reflecting off the end and bouncing back and forth. And then what he's saying is if you were then to put it into motion, you disrupt the pattern. So you still have a kind of a standing wave, but it's now kind of moving, and it has a more complicated waveform. And he associates this waveform with the de Broglie matter wave. So he's saying this is essentially a kind of a macroscopic version of the de Broglie matter wave. And so I'm covering everything I wanted to cover. Right. Yeah, so you can imagine this is a freely propagating photon in a zero curvature vacuum, which has zero rest mass. And you trap it between two Bragg mirrors in a phase-locked cavity resonator, and it acquires effectively, it acquires rest mass. And a light beam, when it reflects from a mirror, you get momentum reversal, which cancels the momentum of the incident wave. And he's saying that the resonator mass motion, it represents a disequilibrium or a dissonant state. If we think in terms of harmonics, you have a consonant and a dissonant state, and this dissonant state is this more complicated wave in the third level. So this is not a terribly clear diagram. It's trying to illustrate the behavior when you apply an external force. And at the first stage, you're at t equals 0, t0. And you're applying the initial push from the left. You're creating a blue shifted wave, which then hits the right-hand side. In the middle, you have the situation at t0 plus delta t, where delta t is the length of time it takes to go from left to right. So you're kind of at an intermediate stage. So you're saying, okay, you're sending a blue shifted wave to the right, a red shifted wave to the left, and they build into or create a contracted moving standing wave packet, as he has here. And so you can associate the various, the modulation envelope wavelength and the speed and so on that you should get given the initial force that you use. So what he's saying here is that the motion of a confined closed-loop electromagnetic wave exhibits inertial characteristics due to what he calls self-referral dynamics. So this is the back and forth interference. So when you apply an external force, the blue shifted incident wave exerts an excess radiation pressure on the reflecting wall on the right-hand side, and the red shifted reflected wave exerts a decreased radiation pressure on the motive wall, the left-hand side. And once set in motion, the wave system remains in motion until you are acted upon by an external force. And the de Broglie wavelength represents a matter wave generated by the motion of matter. So as shown, the wave medium corresponds to an ordinary positive index of refraction. So you get a phase velocity propagating in the same direction as the group velocity. And for a negative index of refraction, metamaterial, the phase velocity propagates in the direction opposite the group velocity. So you have what's called anomalous dispersion. And for a non-dispersive medium, so this is where there's zero refractive index, the phase velocity equals the group velocity, and the Bragg mirrors approximate perfectly reflecting conducting surfaces. and don't reflect all frequencies. So you're eliminating any other frequencies. And so what he's saying from this is that matter, or fermions in particular, consist of stored electromagnetic energy within resonance structures like electrons, protons, atoms. And this self-referral dynamics of stored electromagnetic radiation within a cavity resonator in motion creates de Broglie matter waves, or at least the macroscopic equivalent. And once set in motion by an external force, it continues in motion in accordance with Newton's second law. And nodal displacement due to phase and/or frequency discordance results in resonator mass motion. The thrust is proportional to the internal radiation pressure imbalance. So obviously, the more you imbalance, the more you push, the faster it should go. And just to clarify that, then in this case, what we're using here, we have a single signal generator. We're going to use this to try to move the cavity resonator. And what are you saying here? This obviously has similarities to the Roger Scheuer EM drive, and also the Canet drive, and a few others. And what he's saying is that a major stumbling block in the demonstrations of these kinds of reactionless microwave drives to date is you get extremely low thrust because because of the single frequency magnetron excitation of a few gigahertz. The resonator walls, which are free to move, tend to settle in at the node points. And with a single frequency excitation and its associated harmonics, oppositely directed nodal displacement occurs only when changing frequency modes. And standing waves stay put with the end nodes at the boundary walls. And the resonator will then just kind of jitter in place with no dissonance or net motion. Motion involves alternating jumps between consonant and dissonant ratios. I was also thinking on this also with what Roger Scheuer has said about his drive, is that it actually requires a load in order to work. So that did make me think that maybe he is onto something here, because for the Scheuer drive, you have to have something to push against, so that it's not simply down to the presence of a single signal. So this made me think maybe there is something to this. And yeah, in fact, Larry Reed has also said that non-uniform field effects that are associated with asymmetric frustochronicle resonators are minimal due to the very modest electromagnetic field intensity gradients and the nonlinear polarization effects that are developed for the given low energy input conditions. So I think he's also saying that the amount of energy you're using is also important. So what he's proposing is to use, in essence, to use a resonator at each end, a signal generator at each end, and one which provides a blue shifted version of the wave, and one in this case on the right, which produces a synthetic red shifted wave. And with these two resonators, with two generators, you can produce whatever kind of moving standing wave or de Broglie wave you want. So what we're essentially saying here is, instead of using an external force, we're going to mimic the effect of an external force artificially by internal manipulation of electromagnetic waves. What he's saying here then is that mass transport is affected by varying the phase and/or the frequency difference of the two counterpropagating waves. So you get a moving standing wave. And this is the inverse of what the naturally occurring Lorentz Doppler effect associated with motion. He refers in his work to what he calls the Lorentz Doppler effect, which I assume, from what I can tell, is effectively a relativistic Doppler effect. So it's a Doppler effect taking into account special relativity. And what he's saying here is that we should be able potentially to create an inverse version of this, in the same way that we have inverse Doppler effect, inverse Sagnac effect, inverse Faraday effect, inverse Compton effect. So there are many, many cases in physics where an inverse of an effect exists. I know most famously, I think what we discussed in my last presentation was you have the inverse Barnett effect. So you have, which is also called the Einstein-de Haas effect. And so he's saying that if these effects have an inverse in nature, then in theory we should be able to produce that inverse effect ourselves as well. And essentially, this is what the rest of the presentation relies on. If this isn't true, if this can't be, if this isn't a valid idea, concept, then none of the rest of it really makes sense. So we are proceeding on the assumption that we can induce an inverse effect to the Doppler effect. And so what he's then saying is that a single standing wave is sufficient for limited applications where the velocity is much less than the speed of sound. However, an internal wave system lacks the means to affect uniform acceleration of the surrounding medium to minimize dissipative energy losses in observables. So to minimize things like drag, noise, shock waves, a localized zone, which is external to the resonator, on the order of the length of the resonator, it needs to be kind of managed or provided for. And also, there's no way to avoid excessive stress or strain on the resonator when acceleration or deceleration is applied over too short of an interval. So if you're colliding with something, you would have a sudden jerk, which obviously would damage, unless managed, it would damage your system. So to avoid excessive jerk, you have to ensure uniform acceleration of the resonator and its surrounding medium to avoid the effects of strain, essentially, on the vehicle, on the device. So you need to generate these matter waves internally and externally with gentle changes of the frequency ramp rate. And so what he's suggesting here is to use 3 or more signal generators, which are overlapping they're creating a phased, overlapping, multi-band, swept frequency wave system or harmonic in what's called a Shepard-Risset glissando sequence. And the forcing function inputs include phase and frequency difference, offset interval, a sweep period, and ramp rates that precisely control the acceleration. And up chirp provides acceleration, and down chirp provides deceleration. Now, a Shepard tone, which is named after a guy called Roger Shepard, in audio terms, it's a sound that consists of a superposition of sine waves that are separated by octaves. And when you play it with the bass pitch of the tone moving upward and downward, it's referred to as a Shepard scale. And this creates an auditory illusion of a tone that seems to continually ascend or descend in pitch, yet it ultimately gets no higher or lower. And a guy called Jean-Claude Risset, he subsequently created a version of the scale where the tones glide continuously, and it's appropriately called the continuous Risset scale or the Shepard-Risset glissando. And when it's done correctly, the tone appears to rise or fall continuously in pitch, but it returns to its starting note. And this is used in sound effects in films and things like that. In fact, I have an audio clip which I think play. It's from Wikipedia, and so there should be no licensing issues. I can read out the necessary information here. It's from Wikipedia. User is called Varenk, and it's created under Creative Commons Attribution Share Alike 4 international license. And if you contact me via Tim, I can provide you with a copy of it. It's one of the terms of the license. So I will try to play it. I'm not sure if it will let me. It might be a little bit loud and ear-splitting, so I apologize in advance.
Oh, Rob, I'm not hearing anything.
Okay.
You know what? When you do the screen share, it makes you check share audio separately. That might have been the issue.
Yeah. Okay. It's not important. It's just yeah. If anyone's interested, I can send them the link.
Oh,
it's on
okay. I'm sorry about that. Yeah, I run into that as well. Yeah, it makes you check a share audio box completely separately. So.
Yeah. I mean, yeah. You can look it up on the Wikipedia page. It's on there anyway. So in fact, I extracted it as an MP3, but the original it sounds exactly the same. It's essentially what it's saying is everything is separated by an octave, and you have this continuous change, but it actually the tone never really changes. It's just a way of applying finer control over the system. So it's really just a suggestion. It's not necessarily how it has to be done. So. Yeah, so in this case, if you have say 3 signal generators, you can create a barrage of wavefronts that will increase radiation pressure and therefore the thrust. If you reduce the local velocity of light in a negative index metamaterial, then this may give you an inverse Doppler effect and alteration of antenna radiation impedance and space-time impedance and de Broglie matter waves. So, just set it off again. Ah, right, okay. So yeah, this is kind of to return to an earlier diagram. This is how Larry Reed proposes to essentially perform this function of artificially creating waves of the right frequencies and to modulate them. So, so this is a conceptual diagram for the induced motion of a phase-locked resonator with a phase conjugate reflector, which is irradiated by amplified Lorentz Doppler shifted pump beams, which modulate a standing wave, which then generates a ponderomotive force. A simulated Lorentz Doppler effect results in a contracted moving standing wave, which is what you see in the third level there. Pump beam energy input provides the kinetic energy of motion. So it's not getting energy from nowhere. It's not we're providing it with energy, and then we're manipulating that in a certain way that mimics an external force. So we're creating a kind of internal force. So yeah, just to summarize then, this is Larry Reed's own table, which he is saying these are the characteristics that you should see from this kind of matter wave propulsion. As you can see, the kind of characteristics he's talking about are the kind of things that we nowadays associate with UAP, UFO, and various sightings. So you can see that he's clearly associating his ideas with. He's suggesting here that that is possibly how the propulsion is performed in UAPs. So yeah, so this is a kind of a messy diagram. It was hard to kind of simplify this. So what he's illustrating here, mainly I'm concentrating on the right-hand side, is he's trying to explain how what's called four-way mixing is used to create a mirror, a phase conjugate mirror in this case. And coming in from the top left and bottom right, you have pump beams which provide the power. And effectively, well, it's probably easier if I use his explanation, that the reflecting boundaries of a resonator cavity need not be limited to conventional mirrored surfaces. The reflectors can take many forms, like magnetic mirrors, retroreflectors, phase conjugate mirrors, and so on. In a conventional mirror, a reflected electromagnetic spherical divergent wave from a point source remains divergent, so it just spreads as it reflects. If the wave is reflected from a phase conjugate mirror, the wavefront is inverted in a convergent beam back to the source in a time-reversed replica. Phase conjugate wave generation can be accomplished by 3- or 4-way mixing in photorefractive crystals, in nonlinear optical Kerr media, or metamaterials. 4-wave mixing is a nonlinear effect arising from a third-order optical nonlinearity described by a susceptibility coefficient in a Taylor series expansion, resulting in induced polarization of electric field strength. So in other words, you're feeding, in this case, 3 beams into to create an effective reflective surface, virtual surface for another beam, which you can then modulate the frequency of. And nonlinear phenomena that produce phase conjugation include Broglie scattering, Raman scattering, Kerr 4-wave mixing, resonant 4-wave mixing, photon echoes, that kind of thing. A Bragg reflector is formed from an interference pattern in the overlap zone of 2 counter-propagating beams. So this is what we're describing on the right-hand side here. The effect is similar to conventional Bragg X-ray diffraction from crystals, where atomic lattices form periodic scattering centers. A signal beam that's incident on the interference pattern results in a reflected phase conjugate wave propagating back along the path of the signal beam. And this is a diagram here which illustrates the phase conjugation 4-wave mixing process for a case where the pump beam frequencies are not the same. So you're able to manage the frequency of the wave that comes out. Now, so this table or set of diagrams really summarizes the behavior of phase conjugate mirrors. So using pump beams of different frequencies, you can engineer things such that you can downshift frequencies. So you can go from a normal beam to a redshifted beam, or from a blue shift to a red shift. So overall the downshift, or zero frequency shift, or a frequency upshift by managing your pump beam frequencies. So this shows all the various possibilities. And as a kind of a full-up system, I'm not sure how clear this diagram is, but essentially what he's got is, you recognize the central de Broglie matter wave being reflected to and fro, up and down in the middle, and two sets of three transmitters producing pump beams of different frequencies, which supply the energy and the frequencies, the necessary frequencies to manage the matter wave in such a way that you create, in theory, synthetic thrust. So you now have your system, I guess, in say that, yeah. So just to kind of illustrate this, it's the high internal radiation pressure, which is provided by high frequency standing wave modulation over a wide frequency range. You have amplified, synthesized Lorentz Doppler shifted pump beams, which modulate a standing wave in a phase conjugate resonator to generate a matter wave, which induces motion of the wave system. And then the energy of motion then is proportional to the number of frequency pairs. The frequency sweep rate is proportional to the frequency difference in sweep period interval. The wave system motion is in the direction of the frequency gradient. The starting and ending frequency sweep rates may be adjusted as desired to decrease the onset of acceleration and deceleration. So that reduces inertial stresses and strains. And this is akin to gently curved freeway on or off ramp. So you can ramp up and ramp down gently. And so you have your device, in theory, your propulsion system, but you also need to protect it if you're going to house it in something which is going to travel. And also if you have occupants, you have other delicate machinery or electronics, you need to look into how you're going to protect that from the sort of hostile environment that you're going to produce or going to be present in. And what he suggests, this is Larry Reed's own diagram, and he's suggesting that you employ what's called a whispering gallery mode resonator. So this is where, well, historically sound, but also any kind of wave can be kind of trained to go in around a suitably curved area. Now, he's also saying this is something which can be done with negative index metamaterials to redirect either, well, in the bottom left, he talks about the gravitomagnetic permeability. So that would assume a metamaterial which also has a high gravitomagnetic permeability, which may or may not be possible. This is, I suppose, speculative at this point. But on the upper right is, I suppose, more of interest in that this is more about redirecting electromagnetic energy, and again employing what we call the inverse Lorentz Doppler effect, that waves could be routed around a sensitive area, whether it's within a craft or in space. So yeah. So yeah, in fact, on the right-hand side, what we have is a geometrical model of an EM cloaking field in which energy flows directed around an object. A positive mass object is enveloped in a medium of negative refractive index, deflecting the incident radiation away from the central mass. So it's the opposite of an Einstein ring that you see with often with black holes and so forth. So a negative index metamaterial can serve to induce an analogous electromagnetic flux distortion effect to. So I think you can probably clearly see what he's going for here. In Larry Reed's work, he often shows how his ideas can be incorporated into well-known shapes and objects. In his book, there are many examples of the classic flying saucer, where he's used that as a base to show how his propulsion ideas could be incorporated in something. And in this case, this is obviously his take on the Tic Tac. So what we see here is that you are protecting your system, your propulsion system, using a metamaterial and as a resonator. And this is what he calls the whispering gallery mode oscillator, and carrying evanescent waves. These are extremely near field electromagnetic waves, as a way of, again, managing or generating the de Broglie matter waves around the outside to help to protect the craft or the device. And so just to summarize here, he's saying that increasing the magnetic permeability of a negative index metamaterial, it will reduce the local velocity of light and results in an inverse Lorentz Doppler effect. So this is the reason for the enclosure being a metamaterial. And so this metamaterial external whispering gallery resonator encloses an internal phase conjugate matter wave resonator, as we've seen in previous slides. And it may conceivably be used to generate broadband evanescent near-field matter waves with inverse Lorentz Doppler effect, which will accelerate the surrounding medium. And the inverse Doppler effect results in an energy flow which is opposite to the direction of the resonator motion. And kinetic energy is imparted to the surrounding matter by the artificially generated de Broglie matter waves, and it augments the ponderomotive thrust induced by the internal phase conjugate resonator, which imparts motion to the resonator assembly. In each case, the kinetic energy of motion is provided by the amplified Lorentz Doppler pump beams, which modulate the signal, and phase conjugate beams, creating synthesized de Broglie matter waves. So he's just kind of reinforcing the point here that by choosing, by the selection of an appropriate medium for your generators, for your creating matter waves, that you can manage the direction that they travel, the direction of force and thrust that you get out of each one. Right, now the next slide, I wasn't in my original presentation, but after hearing what the next presentation is, I thought this might be quite fun. As I said, Larry Reed is quite keen to put his devices into classic shapes. So in here we have the classic triangular, or TR-3B, I guess, where he's inserted his own propulsion methods. So at the three corners, he's essentially repackaged essentially the core means of propulsion into a sphere. And in the center, he has some kind of attractor or repulsor beam, based on the same kind of principles, but I'm a little bit dubious about that. It seems to require a Bragg interference grating at the focus in order to actually work. So I'm not sure it's really very practical. But certainly the propulsion at the three corners is something which Larry enjoys doing. He's either doing it as a classic flying saucer, or a tic tac, or a flying triangle. So I thought you might enjoy that. So yeah, so for me that's the end, and thank you very much for listening.
Rob, that's amazing. That is amazing. Wow, like seriously in depth. Okay, so let me do this. I want to remove the spotlight. I am going to, let me see. I'm going to stop your sharing there.
Yeah.
Okay. And I want to put the very first thing, I want to put this thing on gallery view. Everyone, please give an enormous hand for Mr. Rob Chambers.
Thanks.
Rob, that was absolutely tremendous. You just kept drilling down. I was like, oh my God, this thing is technical. So
yeah, I tried to make it less technical.
No, it's wonderful though. It's absolutely wonderful. So let's go into Q&A session. We're a little bit ahead of schedule, but that's totally cool.
Okay.
Let me see. Mr. Mission Control has had his hand up. So, sir, let me ask you to go first.
Hey guys, I'm the inside information guy to Davey Boy from Generation Z there. I've been studying frequencies. I'm an occultist or a metaphysician. And I've been studying frequencies and stuff like this for a long time. And then I come across Dave Winter's information and been just messing around with some audio and stuff. But real quick, I wanted to let you guys know the main build of the cylinder UAPs. I think that I have the answer to their propulsion. What it is you've got 9 toroidal, pretty much Numidian magnets, or we're coming up with these new materials every day, if you pay attention to the science articles. So like Kagome metals and stuff like that. So
okay, well let me stop you for a second. Do you have a question for Rob? Because that's kind of where we're at.
Oh, I'd like to know if he's familiar with what's going on with the Havana NextRad spiral signature we're getting off the Doppler, off the, like, windy radar satellite, because they're obviously heating the ionosphere and pulling that cold air down for the last month. I've got screenshots, and I also want to know if he's familiar with monitoring CERN's activities via the BLF Cumania Marconi antenna in Italy readouts.
Haven't come across
and the effects to the Schumann resonance be with what CERN's doing. And do you know about the quantum gravity experiments they're fixed to pull off or attempt? Maybe do it now.
Okay.
Which they say will inherently change our reality of time. If they didn't already do that in 2012.
maybe.
I'll yield the floor.
Okay. So yeah, Rob, do you have any thoughts on those, or?
No, I've not come across any of that. No. So yeah,
okay. Yeah, and those are things worth looking at. But so let me go to Daniel Whiteson next then.
Hello.
Hey, Daniel.
Thank you
there
very
you
much. So I'm trying to understand the basic mechanism of this propulsion. It seems to me to be equivalent to trying to push a box from the inside. How do you provide an external force using only internal forces?
I think, as far as I understand it, the idea is that you mimic the effect of an external force by manipulating the wave inside. It does sound kind of like pulling yourself up by your bootstraps. I will admit that.
Does not violate conservation of momentum?
Well, I think there is. Because I haven't studied it in great depth, but he does mention something about that the momentum is cancelled out, because a light beam, when you reflect it from a mirror, you have momentum reversal, and because you're doing it at both ends, it cancels out the momentum. Again, I'm not clear on the details. I'm not. Essentially, I think the problem that I found looking at it is that you're creating a wave that goes, one generator goes one direction, the other goes the other. What happens to the energy of that wave when it hits the other side? Because you're not directly using that wave to bounce back. You're artificially bouncing back another wave. So
but it's all
I think
internal, right?
There may be a question of what happens to that, to the wave that you're producing when it hits the other side, unless it's somehow being reused and redirected. Now they're feeding energy in. The idea is that you feed energy in all the time from these pump beams to create your full wave mixing.
But if you're inside a spaceship and you throw a tennis ball on the inside wall of the spaceship overall doesn't move, right? I mean, there's a basic principle there they seem to be ignoring. Yeah,
I mean, this is the thing, is that what he's saying is that you can induce this kind of distortion, this kind of standing wave mixing by applying an external force. And so it does sound, you could call it, I don't know, cargo cult maybe, that it's if you then reproduce the effect of an external force, that it should then have the same effect as that external force.
But that violates conservation of momentum, so it can't, right?
Yeah. This is where I'm not 100% sure myself about what happens to the energy that you've produced when it hits the other side. Where does it go? Is it being reused, redirected in some way?
So my understanding is that every attempt to produce this in the lab has failed. So
Yeah.
I don't understand what the
Yeah, I mean,
basic idea is.
yeah, I think what he's saying here is that if you have like the Scheuer drive, which is just pushing from one side, you have one generator, that it will not, it requires basically some sort of external force, which Scheuer himself has said.
So how is it a
yeah.
propulsion system if it requires a separate external force? That's just
Oh,
an
well,
inert object, right?
That's what I mean. This one doesn't. This is what Larry Reed is saying. This is the advantage of his system over others, is that you are, instead of just sending a beam in one direction, you're mimicking the effect of an external force. And admittedly, yeah, it does. I'm dubious about it myself. I just thought needs a wider audience, really. Yeah, so what he's saying is, as an extension of, if you assume this local generation of inertia, the de Broglie matter wave, his description of it, or that there is a macroscopic equivalent, that he's saying that if you can, if you characterize that form, that waveform, as applied by an external force, if you were then to reproduce that waveform in the same situation without applying an external force, but by supplying it with energy and however much energy it requires to do that, that you should, in theory, assuming there is such a thing as the inverse Doppler or effect in this context, because I think there have been some experiments which have shown an inverse Doppler effect, but I'm not sure it's in exactly the same kind of context as this. So I think this is just his idea. It hasn't been tested as far as I'm aware. So, but it's something which doesn't seem to be too difficult to kind of just to see what the effect is, to see what happens if you can actually, if by mimicking the wave that you would produce, whether it would produce
Well, thank you for the frank answer. I appreciate it.
Yeah. Okay. Thanks.
Awesome. Well, and thank you as well, Daniel. Let me go to Michael Boyd next. Michael?
Hey, I think Jeremy was ahead of me, actually.
Oh, it was, well, no, it shows you ahead of him.
Oh, okay.
I think you beat him to it. Go for it.
So I got a question about dimensions. What's the length of the cavity that you're talking about here?
He doesn't really specify length. I'm guessing a few meters would probably be enough.
A few meters?
It doesn't have to be enormous or tiny.
So I've worked with a linear accelerator that's about 18 inches, and the cavities get smaller the closer the basically what you're creating is a standing wave in each of the cavities.
Mm-hmm.
And then as the cavity gets narrower, the speed of the electrons increases to closer to the speed of light. Mm-hmm. Then at the narrowest cavity, there's the one I worked on, there was a piece of tungsten metal, and it created what's called Bromström radiation, and it was a 6 million volt X-ray. So, I mean, obviously you can use it to create a whole lot of energy.
Yeah.
What I don't follow is how you create thrust or inertial energy, which in my mind is something different from electromagnetic energy.
Yeah, I think this is the equivalence they're trying to draw here, that you feed in energy from these pump beam transmitters. So there's no requirement that it has to power itself, that you are powering it externally. And the magnet, I guess the difference between the blue shift and red shifted frequencies gives you the kind of magnitude of the thrust you should expect to see. I think that's what he's driving at there. Because obviously, if you look at an electron has a huge amount of energy in a very small space. And so he's saying essentially you should be able to scale that up. I mean, I'm not sure what levels of power would be needed to move it at, say, the speed of sound, but I guess that could be calculated.
Well, I know, for example, with a proton, you need a cyclotron to spin it up to get enough inertial energy to get to the speeds of light. So the other issue in my mind is the relationship between the mass of the proton and the mass of the electron. The electron is what, 1,640 times lighter than the proton?
Yeah.
So how do you get inertial energy out of that little mass?
Well, I think the idea is that the inertia comes from the fact that you've confined electromagnetic energy into a very small space. That is the reason why it has inertia. That just pushing against it, it resists your push, and that resistance is a direct product of the fact that you trap this wave, and so it's a direct one. Well, not, I suppose, not one-to-one. It depends on your choice of unit, but there presumably there could be, you could imagine some scale where you have 1 Newton of force. It relates to however many, giga electron volts of energy, or I mean, that is already mass is effectively measured in electron volts, and so I think it's really just a case of a choice of unit. The central concept is that, and as I say, if you read the original article from Jennison, that he can derive E equals mc squared and F equals ma at the same time from this system. I'll post a link to these articles in the chat later, so you can have a look. But even it's just a classical calculation. There's nothing very complicated about it, which is the amazing thing for me. And I think for people like Mike McCulloch, this is why he was so surprised when he read it, because it's like, this is so, it's applying known physics, classical physics, in such a kind of a simple way that you get something very profound out of it. That it's a kind of it's a very attractive idea. So I think there's no real issue with the local calculation of inertia, in terms of the papers that were produced were peer reviewed, and in fact Jennison himself was very humble about it. He said, well, I'm probably not the first person to realize this, but I'm the first one who wrote it down. So he's saying this is so kind of blindingly obvious that probably every other physicist can think of it, but they just never, it was so simple they never thought to actually write it down anywhere. So
So thank you for answering my questions. It's appreciated.
okay.
Great
Awesome.
presentation.
And Michael, thank you as well. Let me go to Jeremy Reese next. Sir?
Yeah. I'm not sure of the exact values, but as I was saying earlier, the information that I've used for the presentation is I've trimmed out a lot of the more detailed calculations. So if you search out, or I will put in the chat later, the Larry Reed's own work, he's included all the calculations that he's used to the variations of phase velocity, group velocity, the ways that it's affected by the refractive index. And I assume that the transmitters that are used are just pretty standard microwave transmitters. There doesn't seem to be anything particularly complicated about it. That they're just, they have to be manipulated, very precisely in terms of the frequency shift and phase shift to get the desired effects, but to get nice smooth acceleration, deceleration, and so forth. So the exact calculations are all in there in the EM propulsion drive presentation. by Larry Reed. There's one in his ResearchGate and in academia.edu. In his book, he actually doesn't really cover it in great detail, but in the presentation, there are pages of calculations. So I would advise your viewer to look at those. But I say I'll put things in the chat later that will point you in the right direction.
Awesome. Yes. Thank you for your answer. And sorry, my audience I was muted for them, but you guys could hear me. So
yeah.
All right, awesome. Okay, well, thank you, Jeremy. Let me go to Jarod next. Jarod?
Hey, Rob, great presentation. Two questions for you.
Yeah.
One, with all of these resonant cavity type propulsion devices, it always seems like the quality factor, the Q factor, comes massively into play. If it's not above like 10 million, you're going to be pumping in way more juice than the amount of propulsion you're going to get out. I didn't really hear you go over any part of that. Second part of the question is, you were referencing like McCulloch's work with it. The dynamic Casimir effect also seems to be a very important component in a lot of this, and I didn't hear you mention any of that. Could you talk a little bit on how that factors into stuff?
Yeah. Right. Let me think. Yeah. So sorry, the first part of your question.
The Q factor.
The Q factor, yeah, sorry, the Q factor, yeah. I think that is specific to the kind of the Scheuer type drive where it's the radius changes, the curve, the sides, the width of it changes from one into the other. And what Larry Reed's, I think he's saying his operates on a different principle. That it's almost like by accident that Scheuer and Canet and people like that, that they have something which sort of works, but works a little bit, and he's saying that actually the Q factor is kind of irrelevant to his idea, because his idea is fundamentally that you're just sending a wave back and forth, and you're just changing the shape of it, and to mimic or potentially, I suppose, create a de Broglie matter wave that moves in a way. So his whole concept is different, although the basic elements are similar. His kind of idea of how the whole thing works. He's saying that, well, this is why it works, and this is why theirs doesn't quite work, or the Q factor is kind of it's not relevant to his work as far as I can tell. Now for the second part, I only really mentioned Mike McCulloch's work because he had looked at this paper as well, the article about the electron. So I'm not sure what bearing it has on his own work. I haven't really looked into the links between that and QI, although I think he has used it as he's given QI as kind of an explanation for why this works. So he's considers that supporting evidence for it, but I haven't really looked into that in detail. So thanks.
Awesome. Let me go to Harold Tavares next, sir.
Oh, hey, thank you for the presentation. And my question has to do with the vector sum of the forces within the cavity. But first, I want to thank you for providing that PowerPoint ahead of time to review on that it was put on APEC website. Now, to my question is, I noticed the inside the cavity, you have a wave generator on the left. Let's say call a wave, the forces on A, that is sending by Newton's third law a wave to the right. So look at a Newton's third law, action sending the wave generates a reaction. Now, when the wave hit the wall on the right side, then you have the wave is giving momentum to the wall. Let's say it gives 50% of the momentum, and then it bounces back to A. So you have now that the equation should read the forces on A minus forces on B, and then you have a net that would be toward the left side, because you have the force of the reaction minus the momentum spent on the wall, and then you have the Q factor of the cavity that is bouncing back and forth. And let's say 50% went to the right wall, and the other 50% is spent, let's say, bouncing back and forth. Now, how do you explain that? Because by all reasoning, by standard physics, it should be a net zero. But when you look at Newton's third law from that viewpoint, the forces there should be a net force toward the left and not toward the right.
Yeah, this, as I was saying earlier, this is kind of my concern, is that you're sending one way, a blue shifted wave to the right, and you're then artificially sending a red shifted wave to the left. Now, I'm not sure what happens to that, the energy and the momentum of those waves when they reach the other side. It's not clear to me if it's somehow being redirected or reused in this four-wave mixing process. I guess, I'm not an expert in this field. As I say, I'm really only presenting this because Larry Reid himself doesn't want to present it at APEC for his own, I don't know, for his own reasons. So I'm just hoping to kind of give this a wider audience. I think the idea is that that energy is redirected or reused in some way. It's not. I mean, as I say, he mentions here that he says that the light beam will undergo momentum reversal, so it cancels the momentum of the incident wave. But my concern is, what happens to the energy of each wave when it hits the other side? So that for me could be a limiting factor here, why it may not work. The idea, essentially, he's ignoring or has otherwise compensated for what happens at the ends, and he's essentially generating a matter wave of the right shape that corresponds to an external force. He's saying that we can effectively create an internal force by mimicking the effect of an external force on the shape of this standing wave. So he's not concerned or has somehow already taken care of what happens at the ends. And he's saying, no, just all we're doing is modifying this wave in the middle. And that, in theory, as I say, if it is an inverse Doppler effect, if that is possible in this situation, then in theory it could create a thrust in one direction. But yeah, I think for me it's still an open question about what happens to the momentum of the two individual waves, because the idea is not that you bounce the same wave back and forth, but you generate one wave one way, another wave the other way, and they interfere or create a standing wave in between. And what happens to the wave at each wave at its destination, I don't know.
Well,
I'm assuming it's somehow involved in the phase conjugate mirror reflection.
because I have done an experiment in that area, I know that the standing wave is not necessary. I mean, I stand by, that it should be on the F8, it's kind of a different, the equation that you have there on the website. The net would be B minus A, and I say actually it's the other way around. But the standing wave does not play very much of a role. I mean, you have a role of destructive and constructive interference in there. But because I've done the experiment, and I know, and beauty is that I videotape my experiment, so I know it's going to be on the A side, which is the argument I have against the M drive Roger Sawyer, that in some situation I think he has a backward. So has he taken into account the role of constructive and destructive interference on the wave in the cavity? What would happen there?
I think, as I say, I think his work is focused to create a moving standing wave of a certain shape, certain phase.
Solitone.
Yeah, I suppose. Yeah, and he is associating that with the de Broglie matter wave. He's saying this is what's sometimes called the pilot wave, de Broglie-Bohm wave. It's either that or it's a macroscopic version of it. And he's saying that if we can create a moving standing wave, not a static standing wave, but a moving shaped wave, that it's the same shaped wave you would get if you pushed it externally. So I suppose if you had a single generator inside the cavity and then you pushed it artificially yourself from outside, you should see this matter wave forming. And he's then saying is that we can artificially generate that same shape of wave inside. And admittedly, it sounds like pulling yourself up by your bootstraps, but he's saying that if this represents an inverse Doppler effect, that would allow it to shift itself. You're still supplying it with energy from external sources, so it's not propellantless. It's not a free energy system. It still requires energy, but it can somehow move itself. Yeah, and I agree. There are unresolved issues, I think, around what happens to each signal at each side, because he doesn't want to bounce it around. He's actually artificially just sending two waves and then absorbing them or redirecting them in some way at the ends. That's my understanding.
Thank you.
Okay,
Thank you.
thanks.
That's a good explanation to think about. Thank you.
Okay.
Awesome, Harold. Thank you. Let me see. Let me go back to Michael, sir.
So I'm just like thinking about this, and so for example, it seems if you had a resonance state where you have two waves, say you have a 3 hertz on one side and then 9 hertz on the other side, you would get basically you get a resonance state there, because you could fit basically 3 of the 9 hertz in 3 hertz. So you could get a resonance state there at 9 hertz, and that would occur on the side where the 9 hertz is. You get where I'm going with this? So
Yeah.
you could make one side energy, basically have excess energy. The question is getting it to be inertial energy. So basically assuming that inertia and electromagnetism.
Yeah, I think because this is what he's saying, is that by the degree of how far out of phase the two waves are, that is kind of in some way proportional to the amount of force you're pushing it with.
Right. Well,
So,
actually, you have to have constructive interference between the two, and so basically there would be constructive interference between the 3 hertz and the 9 hertz wave. But,
yeah, I'm just thinking. I'm just going back to the notes, because he did mention something about the difference between consonant states and dissonant states. That that this is. I forget the exact terminology, but I will just see what I can find. Because again, he obviously understands this a lot better than I do. So, yeah. So right, okay. So, moving standing waves within a cavity resonator in motion, they become contracted. The resonator mass motion represents a disequilibrium or dissonant state, as one or both standing wave end nodal points are displaced from the end walls. So it's when you're trying to displace the nodal point away from the wall, that's where this the tendency then comes. It needs to correct itself, so it's trying to reestablish the node on the end wall. So I think that's.
I see. So it's a phase state, essentially. It's a phase.
Yeah, the thing, you can manipulate the phase as well as the frequency.
Okay. Okay, thank you.
Okay. Yeah.
Awesome. Okay, sorry, let me put your hand down, Michael, and thank you, sir. So let me see, other questions for Rob Chambers? And again, you know what, let me read my thing here. So you can raise your hand in Zoom using Option Y on Mac or Alt Y on Windows. So again, Option Y or Alt Y. Yeah, and again, Rob, your drill down was just amazing.
Well, as I say, I'm trying to do him justice, but I also try to avoid too much complicated equations.
Well, you know, I've talked to Larry Reed. It's been a while, but we talked to him twice, and he said he didn't feel comfortable presenting in public. So thank you for sharing his work. You know, and I think he was pretty, at least with me, he was pretty open about if I remember correctly, he'd said that he went through, basically, he just went through all the literature that he could find, and that was what he was able to pull together, you know?
Yeah.
So.
Yeah. Yeah, in fact, the presentation that I took a lot of that information from, it goes a lot further into gravity as well. He has some theories about gravity and how it relates to electromagnetism as well, which I don't claim to understand, so I left that out of the presentation. I wanted to try to keep it to things that I could get my head around. So yeah, if anyone looks at his work, there is a lot about gravity as well, which is above my pay grade at the moment. So
Yeah, no,
yeah.
I loved his book. I mean, it's incredibly detailed. He did tons of research, tons of synthesis. There's so much in there. Yeah, and that's why I'm so excited that you're able to present it, because I mean, there was a lot. You know, I wish that he would come on, and who knows, at some point maybe he will. So
yeah. So yeah, I mean, I'm happy to wrap it up now. If, as I say, because it's not really my work, I'm probably not the best person to ask, but I just tried to give it as much exposure as possible.
Okay, well, let me do this. Let me go back to Harold, and we do have Jarod with us, so we could go to Jarod early, or the other thing that we could do is, we've got about half an hour. Mark Sokol wanted to present for MUFON, and he was worried that the presentations were going to wrap up there. So let me go back to Harold really quick, though, and we'll.
One more question. I mean, actually, about two subjects. One of them, what are the thermal dissipation problem that it happened there? For example, the heat of the wave, how the energy is spent, and have you done any thinking about the electromagnetic property of the material of the cavity? What kind of interference that the material causes on the wave propagating inside the cavity? And have you considered metamaterials or something like that? What is the level of research that he has in those two areas right now?
Yeah, in terms of thermal management, I don't think there's anything in his theory about that. I think he's really looking at the fundamental principle rather than a practical implementation. So I don't think he's put a lot of thought into what happens to the heat that you generate. Obviously, you're going to generate a lot of heat with this thing. So yeah, I mean, potentially you could imagine there'd be if this metamaterial that he's using, that he's proposing to disperse, and effectively it looks like it's dispersing energy around the outside anyway. Of course, radiating things into space is not easy. So maybe this is more of an atmospheric vehicle than a space one, because in space, I know thermal dispersion is a big problem, just radiating out the heat. So yeah, no, I don't think he's really gone into great detail about the mechanics and the thermal management.
Has he done any experiment, or is 100% theoretical?
I don't know. I assume it's theoretical. I don't think he describes any experiments in his work.
Yeah,
So
that was the impression that I gotten with Larry, was that it was all kind of on paper.
Yeah. Essentially, the core principle here, as I see it, is that the first half of the presentation, or the Jennison's work, seems to be pretty standard in terms of classical physics. Even he's published several papers around this topic, and they're all peer-reviewed in major, respected journals. So presumably, in terms of physics, that's absolutely fine and not questioned. Although it's a simple model, it's probably too simple. But Larry Reed's work really depends on whether or not you can achieve the inverse effect, whether you can, as I say, if you're generating this matter wave, can you generate it internally? If you know what it looks like, you know what the waveform looks like, can you generate it yourself? And if you did that, would you then create thrust? So yeah, it does sound like the ultimate in pulling yourself up by your bootstraps, but he's saying that, well, we have all these other effects which have inverses, which exist. So, for example, you can turn a generator into a motor and vice versa. We said the Einstein-de Haas effect and the Barnett effect are opposites. So there is a tradition, there is a accepted set of effects in physics which have an inverse. So if this has an inverse, maybe we could use it. So I think that's his fundamental, his message.
If you use the inverse effect, how's the energy being radiated out of the cavity? I mean, what happens to the energy when the two waves cancel out? Does it become radiation, thermal energy, electromagnetic, alpha wave?
Yeah.
What is it? What happens?
Yeah, that's I don't think that's made clear. I mean, it may be in there somewhere, but I haven't found a clear kind of explanation. But yeah, I think there is definitely an issue with what happens to the energy, especially if it opposes the effect you're trying to achieve. So, will it actually move, or will it just sit there and radiate heat or microwaves or X-rays or whatever, from both ends? So I think there is a question, an unresolved question there. Yeah.
Awesome. Okay, so let's do this. So I want to. Let me see. I'm going to put this thing back on gallery view. Everyone, again, at the end of our Q&A session, let's give a giant applause to Rob Chambers. Rob, you are the man. That was an awesome presentation. I cannot thank you enough. That was a lot to pull together. I mean, you blew my mind. So,
well, thank you. You're welcome.
Yeah. So let me do this. Let me see if I mean we are ahead of time, and that's totally cool. Let me see if Mark is it Mark?
Bit slow here. It's a little bit slow here at the conference right now because everyone's inside listening to a presentation. How about we wait a little bit until all the presenters are back out here?
Okay. So why don't I do this? Do you want me to go to Jarod then and see?
Yeah,
because we have Jarod with us. We can do his presentation and Q&A, and then.
I'd love to see Jarod's presentation. Go for it.
Awesome. Okay. Thanks, man. Okay. So Jarod, we do. Oops. Let me do this. I'm going to ask Jarod to unmute. Okay. Well, actually, you know what, Jarod? But before you do that, let me stop your screen share. Let me do a brief introduction. Okay. Okay. Here, I'm just going to stop your sharing. So, okay. Sorry about that. Yeah. So let's welcome Jarod Yates. Now, what he's written is from November '89 to April 1990 in Belgium. There were over 2,600 reports of large black triangular UFOs. Then in 1997, Ed Fouche blew the whistle on the TR-3B. This craft was claimed to possess technology that allowed it to hover indefinitely. In March 2022, Sal Pais gave his first public appearance where he details the Navy patents, which include plans for a TR-3B-like airframe. So in this presentation, Jarod is going to propose a few avenues that might help us realize this technology. So everyone, let's welcome Jarod to the call. And Jarod, if you would like to get started, sir, thank you very much for attending and presenting.
There we go. Hey, everybody. I have a lot on this show. The first half is going to be mostly just introducing a bunch of concepts, and then I'll get to the good stuff with the TR-3B stuff more towards the middle. So, different ways that we can realize TR-3B and or warp drives. First, a little background about me. I spent 11 years in the Air Force, the Air National Guard. I was doing F-15 integrated electronics, avionics, the same job that Ed Fouche had for a while prior to going to Area 51. From the Air Force, I got an associate's degree in integrated electronic systems from the Air Force. While in the Air Force, I was studying electrical engineering. When I left the Air Force to go pursue physics, I did a couple years of physics. And then since leaving college and going back into the commercial sector, I've continued some education with electrical engineering. Currently, in the commercial sector, I work in aerospace as a mechanical electrical engineering technician. Also, just as an aside about me, I am very heavily involved with Charles Crawford and Todd Desiato and Jeremiah with the Graviflyer project. That takes a fair amount of my time. For many years, my motto has been that I'm going to see a warp drive before I die. I know it's going to happen. You just got to keep the faith. It's coming one of these days. So that we can have a shared mental model of what I'm talking about with the TR-3B, for anybody who hasn't seen it, I have shamelessly taken this image from Jeremy Reese's Alien Scientist site, who, by the way, definitely lit the fuse 12 or 13 years ago when he released his video on YouTube about all this stuff. It floored me. It's amazing. Jeremy, big shout out to you. So you can see some of the dimensions here in the upper right. It's about 60 meters by 10 meters-ish, tall and wide. Not all of these images, though, are of the TR-3B. There are some that are of the TR-3A, which use completely different mechanisms, as you can see in the lower right-hand side. Whoops. Also, I think there's some disinformation campaigns out there. There's been some CGI videos released of what people are claiming to be the TR-3B. I don't think that's the case. In the upper left hand, you can see that CGI model. There's a couple other videos of it supposedly flying through Afghanistan, and other videos of it shooting laser beams or gamma ray beams or something and blowing stuff up. I suspect that's all a disinformation campaign. Also, in the lower left-hand side, you can see another image of that TR-3A. That image was actually taken right over my base here at Portland, Oregon, back in 2019. I reached out to some of my buddies that are still working there to say, hey, did you guys see this sitting on the tarmac? Because it would have sat just a couple hundred feet away from where we worked. Unfortunately, I don't got enough contacts there anymore, and nobody remembers it. It was too many years ago. Also, it would have been a night flight, and most of my friends were on day shift. I think that picture was taken sometime around 6 p.m. or so. Also, on the right-hand side here, you can see this is a Google Earth image taken from 2004. I just screenshotted this image on Google Earth a few weeks ago. It's still there. It was measured at about 100 meters on a length on one side, which does not line up with any of our current understandings of the size of this. Its size should either be 200 feet or 600 feet on a side. And this image doesn't quite match that. So maybe it was at a different height, or maybe once again, we're dealing with disinformation, or who knows. Just what I'm trying to say is keep your skeptic hat on with everything with regards to what information you're presented, even including mine. All right, so I got a little compilation I put together here of 3 different instances of the TR-3B that I'm going to try to play now. This image was taken supposedly in 2009, I want to say, over Paris, France. And I got a slowed down version of these light ball resonance modes. You can see that's the first resonant mode. Now in the second resonance mode, notice how the top is slightly different shape than the bottom. It's not a perfect sphere. And the third, we're still kind of wavering in the light ball. It doesn't stay steady, and then just disappears and is gone. This next image, I'm dubious whether or not it's real or not. I think it still demonstrates the idea. The difference is that you don't see a charge up of different resonance modes. It's just a single mode and then it shoots off, which is part of what makes me dubious about it. Also, that looks maybe CGI. This image was taken from military.com, a civilian website. I find it useful for a few reasons. One, you can see that they can orient themselves in any direction, which means that it's Z, it's vertical. Thrust doesn't necessarily always have to be coming from the center of the ring in the middle there. One final thing to note about that is that at the third resonance image there that we see on this first video, when it just flashes and disappears, all of these resonances, we may be dealing with shutter artifacts from the camera that was used. There may have been a completely different thing than the human eye would have been seeing, or that a fast camera would have been seeing. Also, by the way, anywhere where you see on my slideshow something that says link, I have the last few slides will show all of the actual links to these so that you don't have to click on them, you can see it. So the lower left-hand image on this was supposedly taken during that Belgium wave from 89 to 90. In 2011, the guy who released the image came forward and said, no, it was all a fake. I faked this image. Once again, remain dubious about any actual images that you see of the supposed TR-3B. That upper right-hand image that looks quite similar was taken from bbc.com. I think it looks quite similar to that Belgium image, except you can see a lot more detail there. Some observations about it. When the TR-3B is getting ready to shoot off, it's not releasing light just from the lower side, but we see a fairly uniform ball of light coming from all around the craft. Also, the color of the light I find to be quite important. It's not, blue or red or green. It's white light, meaning we should be seeing a very wide spectrum of photons coming off this thing. The shape of it I also find to be useful, since the lower side in the second mode was slightly smaller and more hemispherical than the top mode, or the top side of that second mode looked a little more egg-shaped. That to me may present some useful information regarding how it is producing the lift. It's putting out more energy on the bottom than it is on the top. Also quite interesting is how the size and the shape of that light ball changes as it's going through its resonance modes. In the first one, we can see that the edge of the light does not extend past the craft, but then after that it is. That may once again be an artifact of the camera. The camera is just getting washed out, but I tend to suspect that it's actually somehow containing a ball of light, which blows my mind. Also, and this one really just breaks my heart. A couple years ago, there was a YouTube channel called Redstone that had released a video of the TR-3B, in which in this lower right-hand image from the military.com video, that center white ball of light was in far higher definition. Unfortunately, the video has been taken down. It got taken down within a few months and I've never been able to find it again. But that center ball, it was cavitating in like 3 dimensions. It was squishing together on the sides, spread out, squished together on the top, spread out, squished together in the 3rd dimension. That may have also presented some very useful information as to why does it have a ball of plasma in the middle that is squishing in, uniform and different directions as it's just standing there hovering. The rate of the cavitation of that plasma ball, at the time, I measured it to be somewhere between 1/2 second to 2 seconds. All right, so just a quick overview on what I'm going to be going through here. If you want to have a warp drive, if you want to warp space-time, you're not going to do it with a 9-volt. You've got to have some stupid, ridiculously high energy densities. they may be attainable through orbital angular momentum or spin angular momentum in optics, but I strongly suspect that they're using plasmas for many reasons. Phonons, or instead of photons, you have these packets of mass movement of particles rather than of electromagnetic particles. These may also be used for some negative effective mass effects. Then we can go into the Pais effect and kind of break down a little bit more on what his talk from the 30th of March this year was talking about with the vacuum breakdown, and how you can have some other lesser known effects from the Schwinger effect. And then I will try to improve upon that by showing how we can more readily attain the Schwinger effects using superconductors. And then from that, I'll try to wrap it up with the Bright-Wheeler process, or the dynamic Schwinger effect, which may also help us understand a little bit more on what mechanisms the craft may be using to produce its flight mechanisms. Starting off with some useful acronyms and concepts. If you see anywhere SAM or OAM, I'm talking about spin or orbital angular momentum. I'm going to also describe what left-handed metamaterials are for those who don't already know. One of the most interesting and important concepts that I'm going to try to talk about is something called birefringence. And then surface acoustic waves are also quite useful for some of the negative effective mass from the phonons. So starting off with some spin or orbital angular momentum. If you have spin angular momentum, that's like a particle spinning on its center axis. Orbital angular momentum is a particle orbiting around a center axis rather than on that axis. So like a planet going around a sun versus a planet spinning on its, pole. There we go. A little more about orbital angular momentum. This is how you can apply torque, angular torque, to light or particles. This allows you to achieve much higher energy densities in a more confined space. The plasmas that are described in the TR-3B may be asymmetrically compressed to be able to produce this kind of corkscrew shape you see in the center there. Left-handed metamaterials. These are going to sound kind of like birefringence, but they are slightly different. They can be very useful for focusing as well as just generating superluminal group or phase velocities. Especially important is that lower left-hand quadrant, quadrant 3, where you see what these left-handed metamaterials are. The little E stands for the permittivity, the ability of electrical charge to travel through space. And the U is mu, and that is the permeability, or the ability of a magnetic wave to travel through space. Also, as an aside, in the upper right-hand image, you can see that's for backscattering. I find it extremely useful for all of these things, for all warp drive related things, to think of space-time as a optical lattice rather than to think of it in terms of fields. You have to use fields, but when dealing with reflected waves or transmission of waves, all of my research I find it extremely useful and helpful to think in terms of optics with regards to all of this. Birefringence. So when you have a normal medium for a light wave to pass through that is uniform, the polarization of that light is going to be unaffected as it goes through. If, however, there is an asymmetry to the lattice that the light wave is going through, one of the polarizations is going to be different than the other one, and so it will travel at a different rate than the other polarization. The one that gets the change is called the extraordinary ray. That is the oval shape inside the circle in the middle image. The unchanged ray is called the ordinary ray. On the lower right-hand side, you can see a block of naturally occurring calcite crystal. This has a natural birefringence to it, which is why you see the double image of the grid paper underneath, because one of the polarizations of light is traveling at a different speed, so you get two images. You can get birefringence just by, you get it in Scotch tape, you can get it in glass, you know, in many mediums. If you apply an asymmetric stress to that medium, then you're going to have an asymmetry in the lattice of that medium, which means you're going to have light waves traveling through that at different speeds. You can also get birefringence from something called the Kerr effect, which is like a stress inducement from electrostatic or electromagnetic fields on your medium. So when we're dealing with plasmas, you're going to have very strong Kerr effects because plasmas tend to have very strong electromagnetic fields. One more thing on birefringence, actually a couple more. So the normal birefringence that we saw in the calcite crystal is called positive birefringence. That's where the ordinary ray is traveling at its normal unchanged speed, and the extraordinary wave is the one that is retarded or slowed down because it's traveling orthogonal to the orientation of the cells of the lattice. Where it gets really interesting, though, is something called negative birefringence. And this is like a left-handed metamaterial. This is where your index of refraction for the changed direction is negative. You're having a negative index of refraction, which means you're also getting a negative permittivity on that axis. This is going to come in quite useful down the road in this show. One further thing on that. When you have a negative permittivity, that also means that you're probably going to be getting reflections of the passing ray. Also, I apologize, I forgot to put my disclaimer in at the beginning of this whole thing. As you can see with my educational background, I am punching way above my intellectual weight class on a lot of this. So keep a bowl of salt handy with all of these terms and topics I'm trying to describe, because this is what you get from Wikipedia and white papers. There is another further very interesting thing about birefringence, and that's called kinematic birefringence. So if your material is traveling at relativistic speeds, that will also change because of Lorentz contractions, the ability of that light wave to travel through that medium. And this is how you can achieve negative group velocities or phase velocities. Some very, very interesting things can occur from this. So the second harmonic, or the frequency doubling that you can get from birefringence, is where you're taking the extraordinary ray and you are lining up its phase with the same phase as the ordinary ray. This allows you to double the energy. The photons combine and are now a single photon of twice the energy. And this doesn't have to be done with just a single step. You could have this in a repeating pattern where it goes through one nonlinear crystal and a prism, and you line them up, and then you do it again, and then you do it again. And so you can keep on upscaling the harmonics of your light waves into very, very high energy densities. Just an aside, interesting fact that I came across in all of this, gravity waves can also demonstrate birefringence, and it has been measured. Negative birefringence of gravity waves has not yet been measured, but that may be a matter of time. Also, gravity waves are predicted to be able to tunnel, although I don't think we have observed that yet either. One other interesting aside, a group out of Tokyo, or I think it was Tokyo, they came up with a warp drive idea where you have two separate materials of different refractive indices, with one of those being a negative refraction. And when you pass an electromagnetic wave through it, there's no change in the phase, meaning that it is actually tunneling through the point where those two are touching, which would be a contraction of space, which, hey, we got warp drive. Mildly dubious, but very interesting nonetheless, worth at least a read. I'm not going to play this video, but for the following couple slides, this is very helpful. Whenever I'm talking about superluminal phase velocities or superluminal anything, we're not talking about faster than 186,000 meters per second or whatever. You're talking about how shadows can move faster than photons, right? If you take a laser pointer and you point it at one side of the moon and you sweep it over to the other side of the moon, the rate that you're able to sweep that is faster. The distance from the diameter of the moon is greater than the ability of the light to actually go from one side of the moon to the other if you were standing on the moon with a laser pointer. But what's actually happening is spacing between those photons hitting the moon is just getting greater. Highly recommend watching that Vsauce video if you haven't seen it before. So in order to get superluminal E waves or extraordinary rays with negative birefringent material, they take, you can see the top wave, the omega-1 component there, and the omega-2 component below it. What you have is the ordinary ray is the omega-1 and the extraordinary ray is the omega-2. When these two are combined, you have a packet, and that packet can move just like I was saying, the photons going from one side of the moon to the other. That packet can go faster than the speed of either of those two components, and even faster than the speed of light, but you're not actually transmitting any information. You're not actually breaking causality and time laws when you're doing this, although it can be extremely useful for upscaling the energy of an electron at the forefront of that packet. So surface acoustic waves are kind of like the skin effect in electromagnetism, where the higher the frequency, the more closer to the surface the electro waves are going to travel. The difference being, though, that since we're dealing with matter and not electromagnetism, the depth of these is dampened a lot. You only get about 1 to 2 wavelengths depth when you're dealing with phonons rather than photons. These present a really big problem with soliton research in fiber optics because you get these nonlinear electrostriction events occurring down your fiber optic, and that destroys the soliton that you're trying to get reflecting back and forth. Further about surface acoustic waves, they can have greater density than photons. Because they have more degrees of freedom, they have more possible polarizations. That means that you can get higher energy density from photon wiggling, or from phonon wiggling, than photon wiggling. This I would highly recommend reading while remaining dubious. There's been a few papers published suggesting that phonons, or sound waves, or surface acoustic waves, generate their own gravitational mass, that they actually carry their own amount of mass. It's extremely small. It's ridiculously small. 10 to the minus 24 is beyond anything that we're ever going to measure. However, there may be ways to upscale this into a usable amount, because like I said, you can have a very high density of phonon energy compared to photon energy. That paper from 2019 was reviewed by a guy from University of Oregon in my state. He took a more realistic view of it, and he was able to determine that they may be able to move matter from a more classical definition, but once again, we're dealing with extremely small amounts. Somewhat related, but not exactly the same. This is called the mega drive. This is where they use two masses with a nonlinear damping between the masses, and they are able to produce a net motion from the vibrating of this device. It has been tested and verified many, many times. Unfortunately, it seems like it has kind of gone quiet in the last few years, despite the fact that they have had what I consider to be a significant amount of thrust. 100 micronewtons for something that small is insane. I suspect, though, that the previous example from how phonons can generate their own gravitational mass is probably not responsible for this. This is probably more likely because of the nonlinear damping taking place. Similar to that nonlinear damping, so if you just go on Wikipedia and look up negative mass and plasmas, it suggests that plasmas can also create their own negative effective mass. However, the scientists that have tried to do this run into issues where you can only get negative mass, or you get negative indices of refraction. It's very difficult, near impossible, to attain both simultaneously. All right, starting to get into the good stuff. So the Strategic Defense Initiative, or SDI, came to bear under the under the Reagan administration, although the idea for it had started under the Nixon administration about 8 years earlier. LaRoche was one of the ones who was trying to get it going for a long time. It was responsible for a couple of things called Project Star Wars, or Project Excalibur, or Project Brilliant Pebbles. It was deemed a failure by the public, but that may not have actually been the case. They came up with thousands of useful patents for things, all things related to lasers, and there's been many, many medical advances from the stuff that came out of that. It turned into the Ballistic Missile Defense Organization in the mid-90s, and then that turned into just Ballistic Missile Defense in 2002. So if you want to track where this technology has traveled and who is responsible for what, that's probably a good place to start, is just follow the changes in names. It may have led to a proof of concept for the Schrödinger drive, according to Pais. He did not claim that. I'm saying that. If you try to see anything about SDI and warp drives or anything, you're going to come up goose egg. It's not going to happen, because either it never actually was successful in producing that and it's all been a disinfo campaign, or it was successful, and go figure, all of these resources are very good at making sure that these technologies that they're trying to keep secret stay secret. I came across one interesting SDI report from the early 90s where they were talking about Project Black Star, which was a space plane that Lockheed was trying to develop. They said that it could cause background modification with very high energy releases. However, once again, remain dubious. That was speaking in reference to trying to identify nukes that were being launched. And so it may have been referring to cosmic microwave background modifications from high energy payloads rather than actual space-time background modification. So just another disclaimer for you. Can't talk about SDI without talking about LaRoche. He was an economist, and he was working with the Russians in the early 80s, trying to convince them that SDI would be an alternative to the arms race that was well underway, and that it would be an economic boon to everybody involved. However, once it finally got underway in '83, the Russians broke off all ties, publicly anyways, with LaRoche. And one interesting point about the SDI was that Reagan's Secretary of State, George Shultz, spoke at Ed Teller's memorial in 2003, and he said the SDI was in part responsible for ending the Cold War, which doesn't surprise me. If you are Russia and you want to shoot off nukes, and you know that it doesn't matter how many dummy nukes you put out there with it, that all of them are going to get space lasered out of existence. I mean, that definitely puts a wet blanket on the ability for blowing everybody up. Some scientists that are very important to SDI. You can't talk about any Black projects from the 20th century without talking about Ed Teller. This guy worked at the Manhattan Project. He was pretty high up with Heisenberg. He's called the father of modern rocketry. He was the head guy at Los Alamos National Labs. Interesting aside, according to Lazar, when Lazar was working at Los Alamos, there was a colloquium with Ed Teller, and that was when Lazar walked up to Ed Teller, and Ed Teller just happened to be reading the newspaper with Lazar's rocket car or jet car, and that was the introduction that ended up eventually getting him his 9 visits to Area 51, if Lazar was telling the truth. One of the most interesting people I have come across in all of this research, though, is Julian Schwinger. This guy may have worked on SDI, but if he did, it was tertiary. They had a lot of overlap in the academic world, but it's with SAPs, it's kind of difficult to tell who's working on what. You have to just go off of their published papers and try to see where some of the overlaps in topics that they are publicly disclosing overlap with some of the patents that SDI was releasing. There was a conference for 24 of the brightest minds in the world at the time, a month before Roswell in June of '47. Rockefeller Organization put it together. And Julian Schwinger was the spotlight in this because he was a Wunderkid. He got a Nobel Prize that he shared with Feynman and one other person for his work on quantum electrodynamics. The guy is one of the smartest people that we've had. Also, there was an international conference for lasers that took place that over many years, but Ed Teller and Schwinger were spotlight speakers in '87 and '88 respectively. And in those topics, they're all talking about, or in their talks, they're all talking about the role of lasers for directed energy weapons, and specifically how this can apply to the Strategic Defense Initiative's plans. One other extremely interesting person that I've come across with all of this is someone called Dr. Friedrich Winterberg. This guy was 16 at the end of World War II. He came over in 1959 through Project Paperclip. This guy's still alive today, crazy enough. He teaches out of University of Reno. Don't quote me on the name of the university, but it's the university in Reno that is responsible for like 1/3 or 1/4 of all their projects are super classified. Very interesting guy. Most of his stuff deals with plasma. He also strikes me as a mad scientist. This guy has had many, many crazy out there ideas, helpful contributing ideas on how we may be able to eventually have real space travel. But most of his stuff usually is dealing with blowing up nukes behind ships type stuff, or crazy antimatter reactors that may not actually be so crazy. I spoke a little bit about Project Excalibur there a few slides ago. That was where they were using nuclear pumped X-ray lasers, and then they would accelerate those lasers through a plasma. And this was supposed to be for shooting out nukes out of the sky, but it may have also been used for drilling and making some good underground excavation opportunities. So like I said, Winterberg is very big into everything plasma fusion related. A little aside about plasma fusion, you can't talk about it without talking about something called Alphen waves. These are whenever you wiggle a plasma particle, it's going to produce an electromagnetic field. So if you got really strong waves going through a plasma, you're going to get really strong electromagnetic fields. So I apologize, next couple slides, there's a lot of reading, but I find it to be quite helpful. So I will do so. You can get orbital angular momentum through plasma, like I was saying at the beginning of the show. If you do it through fiber optics, you get something called hole burning, where you're actually burning up your fiber optic the more you twist the light, and that is a problem. And just as another quick aside, I'm also very big into Charles Hall's recounts of the tic-tacs that he claimed to witness when working out near Area 51 back in the 60s. He claimed that over 2 years, he developed relationships with a race of beings called the Tall Whites, and that on one occasion, he actually got to see one of their craft with the panels off up close, as well as seeing many, many flatbed trucks coming in, bringing in thousands of miles of fiber optic cables. And that in his conversations with these beings, they told him that they were using fiber optic cables to be able to generate their flight mechanisms, which strikes me as quite interesting, because if we're talking about using fiber optics rather than plasmas, that means that they would be dealing with big temperature problems with their craft, which it also so happens Charles Hall described. They said that was a major problem, was that they had trouble controlling the temperature and keeping the temperature down on their craft in order to actually get from point A to point B fast enough to avoid bad people. Moving on. So if you don't want to burn up your material, you're going to have to use plasmas because they can handle much higher energy densities and temperatures and all that. Unfortunately, this gets very challenging because plasmas tend to be very, very chaotic. It's very difficult to get actual structures in them. But you can try to do so if you have asymmetric magnetic fields around the plasmas, which when you do that, you can end up getting optical vortices out of them. Moving on to superluminal plasmas. So you can get a massive energy boost of your electrons if they're moving at the wavefront of a plasma that is already in that superluminal group velocities described earlier. These are called plasma mirrors, which I suspect are one of the few major mechanisms that may be at play in the TR-3B. If they are able to generate extremely high charges and magnetic fields from the plasmas, this is how they're doing it, is by having a reflective plasma wavefront moving at relativistic speeds that is then reflecting oncoming laser beams off of it, so that you get really stupid high charges of photons and electrons at the reflection point. So if you suddenly photoionize a plasma, you're going to get a change in its refractive index. It's going to drop from 1 down to 0. You're not going to get any more refraction out of it. Semiconductors, it's a much bigger drop. The electron hole pairs that are instantaneously created when you hit it with a ton of energy cause its refractive index to change from 3.5 to 0. This ends up being something called a chirp. It sweeps up all the low frequencies into a ramping higher frequency modes. In soliton research, once again, in fiber optics, This is the majority of what I have found in anything referenced to being able to generate warp drives with fiber optics. Also happens a lot with lightning bolts. They tend to create these chirps where they ramp up all these lower frequencies by potentially thousands of octaves, getting very, very fast pulses. Once again, highly recommend looking into Vinterberg's research regarding this, as he thinks that sonoluminescence may be responsible for some of these chirps that are actually extracting 0-point energy out of the vacuum whenever you have this sudden photoionization of a material. Here's a useful image when I'm talking about these plasma mirrors. You get a deformation of a flat plane of plasma from a laser beam, a low energy laser beam hitting it from the back. And then when the oncoming laser beam hits the center of that, it's timed such that the snap of this plasma will accelerate the oncoming beam. Moving on to the Pais effect, he, in his March 30th talk, did not delve super deep into a lot of things. He kept saying he had all this secret sauce that he wasn't going to be talking about. I strongly suspect that's because if they were using nuclear pumped lasers or nuclear energy sources, that would be breaking all kinds of international aerospace laws, which, you know, that's kind of a problem if the US is going to get in trouble with the world. Not to mention the potential for weaponization and all sorts of other things that can happen whenever you have nukes in planes that are used for their energy source. His gist on the Schwinger effect is that when you get a high enough energy density to attain the Schwinger effect, that it actually is changing the space-time metric enough that you're getting negative energy densities, or you are able to change the gravitational constant in these tiny, tiny little pockets such that it allows you to produce warp fields. I'm still mildly dubious about his descriptions, and I'll believe a lot more when he tells a lot more. So I've been talking about the Schwinger effect, the Schwinger limit a lot. Here, I'll actually go in and describe a little bit more on what it is. The Schwinger limit is what happens, like I said at the beginning of this talk, if you think about space-time as an optical medium rather than just a nothing vacuum, it can be quite beneficial. So if space-time is a medium, an optical medium that you're punching a huge amount of energy through, like I was saying, the Kerr effect, you get this electrostriction of the space-time vacuum that can occur strongly enough that you're actually deforming space-time enough, you're putting enough energy into it that it's changing the birefringent value of the vacuum. This requires extremely high energy densities, though, that have not yet been attained. Although we are getting very, very close in the academic world, we're still just not quite there. There have been analogs of it, though, that have been detected. We tend to see this effect out in space around things called magnetars, which are neutron stars that are producing the strongest magnetic field known to man. They also tend to be, well, I'll just keep moving on. So when you get all of this energy pumped into a very, very tiny space, all of a sudden these particle-antiparticle electron-positron pairs just spontaneously start coming out of the vacuum. You have altered the value of the vacuum enough that the tunneling energy required for quasi-particles, virtual particles, things that don't physically interact as far as we understand, generally speaking, they're able to tunnel through that energy difference, and now they're actually popping into an existence. An analogy that I could provide for this is, imagine you're standing on a trampoline over a swimming pool, right? And normally just your weight on standing on that trampoline isn't enough to deform the trampoline enough to actually get the water from the pool to come up from underneath it. But if you get a bunch of people standing right in the middle, maybe you can bend that trampoline enough that you start getting water coming up through the grating of the trampoline. That's kind of what's happening with this. You have something called the Dirac sea, which is all the electrons, anti-electrons, it's all the charge aspect of the universe that's existing all around us in numbers that are way too high to even make sense, but they don't actually interact with us because they are in a virtual state. If you change the value of the vacuum enough, they go from being in a virtual state to being in a physical state. And this is amazing to me, that you can produce antimatter from the vacuum if you have enough energy. Just blows my mind. Schwinger is a friggin' genius. So if you go beyond the Schwinger limit, so the Schwinger limit is 10 to the 18 volts per square centimeter, which is a lot. You get something called higher harmonic generation. And this is where it's that sweeping up of those lower frequency waves into higher frequency waves. Because like I said, we're changing the birefringent value of the vacuum. We're changing its ability to transmit frequencies through it. So going back to the plasma mirror effect that I was talking about a few slides ago, you can see that these plasma mirrors are able to upscale these lower incident lasers into extremely fast lasers. We're talking attoseconds. It's beyond ridiculously fast. In, was it 95 or 96, SLAC, the linear collider, they managed to create about 100 pairs of Schwinger particles using this. However, that was inelastic scattering, not elastic scattering. So in order to be the true Schwinger effect, it would have to be elastic. I just think it's amazing that almost 20 years or 25 years ago, they were actually managing to do any energy densities enough to produce particle-antiparticle pairs. That's further in support that perhaps SDI had managed to master this even a few years before them, as secret programs tend to be a few years or decades even ahead of the commercial and academic sectors. Here are some numbers that I got from Ricardo Storti, if he's on. Big thanks for this. I'm trying to describe in this flow tree the different methods that you might be generating enough energy densities to be able to produce warp fields. However, unfortunately, neither one quite gets there. If you wanted to use solely orbital or spin angular momentums from a nuclear pumped laser exciting a plasma, it's not going to quite get there. It's going to be at least half of the way. If you want to use plasma oscillations for that negative effective mass I was saying before, where the phonons are producing 10 to the minus 24 of the gravitational constant, once again, you're still not quite getting there. If you want to actually alter the vacuum enough, you're going to have some crazy asymmetric electrical or magnetic fields that are generating their own thrust, which sounds like crazy sauce to me. Schwinger effect is probably far more likely than using just regular energy densities you get from OAM or plasma oscillations. For the power supplies for the TR-3Bs, small modular nuclear reactors, maybe some of you have heard of these before. These are nuclear reactors that are orders of magnitude smaller than the normal ones that we see and use today. They tend to produce less energy than those multi-gigawatt facilities. These things can produce up into the hundreds of megawatts though. SDI was in part responsible for the research that came into play to be able to make these. Back in the early 80s, they were producing these. If you wanted to have enough energy, half a gigawatt, to even begin to alter the vacuum, this is one of the few ways, one of two ways that I have found that they would be able to do it. Is they're gonna have three of these, one along each leg of the triangle, or they will curve them and make a ring. I'm a little dubious about curving these things because nuclear reactors are hard, and you put curves in them and now they get even harder. So probably not likely. A helpful diagram there at the bottom shows the official record for the laser power outputs that humanity has been able to achieve. You can see by about 1990, officially we were over the terawatt range. In order to achieve any of these energy densities necessary, we would have had to be much higher, probably closer to the petawatt range, which you can see we didn't even really start hitting until around 2000. But like I said, all the resources in the world and all the geniuses in the world at the military's disposal, who knows, maybe they managed to be a couple decades ahead of the curve on this as well. SDI worked on something called Project Sprint, and this is where they were using fuel cells connected to these modular reactors in order to try to get gigawatt production. They never actually disclosed their success of Project Sprint. It's hard to say whether or not that's because it was a big failure or because it was a big success. Like many things with these SAPs, it's real hard to track. One of the most interesting things I have found for the power supply of the SDI programs are things called superconducting magnetic energy storage. This is where you use a superconducting material and you put a bunch of magnetic energy into it, and it can store that magnetic energy until you hit it with a laser, you do something to destroy the superconducting effect, and then boom, it shoots out all of that magnetic energy in an extremely short time frame. As far as I understand the commercial sector, we've only gotten up to like a quarter of a gigawatt to half a gigawatt using these. But an SDI paper from 1989 suggests that they were looking into this for multi-gigawatt energy storage. They would have been using this using magnetohydrodynamic reactors. Another aside, for any of the links that are paywalled, I would never be one to recommend using something to get around paywalls like Sci-Hub or any of those sites, because Sci-Hub tends to be far too useful in these efforts at researching. So definitely, whatever you do, don't use Sci-Hub to get around paywalls. Anyways, let's go on to the next one. The plasma, Mercury-based plasma that Fouche describes, he claims that it's ridiculously high pressure. It's at a 250,000 atmospheres of pressure, or 25 gigapascals, and that it's super cooled down to minus almost 200 degrees Fahrenheit, 150 Kelvin, and that it's moving extremely fast. If you look at the, I think it was the 200-foot model, the 50,000 or 60,000 RPMs that he describes means that it's moving somewhere around 500 to 700 kilometers per hour. I got an image there in the upper right from one of the papers that I've got on this. Mercury has been tested at these conditions, not just mercury, it's a mercury-based cuprate or superconductive material. The fact that this has actually been tested blew me away. I can't believe it. And the red lines that you see in that image are using Fouche's numbers of pressure and temperature. And you can see that we actually have 3 different forms of mercury cuprates that were tested in that. And one of those falls extremely close to the numbers described by Fouche. Extremely interesting to overlap there. However, these pressures are extremely difficult to get. The experiment that I'm just describing there, they were using diamond anvils And I don't think the TR-3B is using diamond anvils. It's probably just using really strong magnetic fields and or compression of the plasmas to get these kinds of pressures. But yeah. One description of a similar type of warp drive using these spinning Mercury-based masses, something called Ford's rotational field. He worked for Hughes Laboratories, and he suggested that you could actually create dipole gravitational fields. I'm dubious about. We haven't ever seen anything even close to indicative that gravitational fields can produce a dipole moment, maybe a quadrupolar moment, but not a dipole moment. And he said that you could accelerate liquid mercury around a toroid, similar to that tokamak image that I got there on the right. And especially that if it's superconducting with a very strong electrical current, that you'll get very high electromagnetic forces as this toroidal field starts to envelop it. Mildly dubious about that. Maybe there's a there. I don't know. I just don't know on that. Now we're getting into the real good stuff. So the Schwinger effect was 10 to the 18 volts, right? How on earth are we ever going to be able to achieve that? Sal Pais was suggesting that there was a secret sauce there, that there's a way that you can actually make this attainable. The superconducting solder Schwinger effect may be the way that this is done. If you have a superconductor, it has a bunch of Cooper pairs in it, and the band gap, the difference, the distance of that trampoline above the water is much, much lower. So you're getting double the number of quasi-particles. You're getting much easier ability to achieve those quasi-particles into real particles when you're using a superconductor. Ridiculously easier. We are able to go from 10 to the 18 volts per centimeter down to 10 to the 8th volts per centimeter, or 100 million volts. And 100 million volts was very readily attainable for many, many of the past decades. That is not outside the realm of possibility like 10 to the 18th volts are. And this has actually been somewhat demonstrated in graphene. And they were using terahertz lasers in the graphene to be able to achieve this. Also, regarding how Fouche was saying that the mercury-based plasma was spinning at tens of thousands of RPMs, that one has always kind of stuck in my craw as to why on earth do you need to spin this stuff? Shouldn't you be able to do it in a solid state? One of two reasons to do this would either be because you are decreasing the band gap further by getting it under even more pressure, or that was one of the ways that they were being able to achieve those super high pressures was through the centrifugal force of that plasma. Another reason would be that is how they are achieving extremely strong magnetic fields. Oh, and just as a side note about this, officially terahertz lasers weren't created until 1995, but Ed Fouche was claiming that the TR-3B was in existence since at least the early 80s. So once again, the potential that the leap of faith that the advancement in technology that was not disclosed must have been in existence. You got to take that leap in order to believe that the TR-3B was as Ed Fouche described. Here's an interesting convergence between effects that I wanted to note. If you have a superconductor and you're hitting it with really high voltages, that sounds a lot like what Eugene Pogplanov was doing. He took a really big superconductor and spun it really fast and then hit it with many millions of volts, similar to what we're describing may have been occurring in the TR-3B. He suggested that there was up to a 2% weight loss. He was only getting 10 to the 6th volts though, and we're saying you need 10 to the 8th volts in order to actually achieve this. You still are achieving it, but at 10 to the 8th volts, it's 100% pair production. Anything below that, and it exponentially decreases in the number of pairs that you're going to produce, which may be why Pogplanov was only getting, a couple % weight loss. still don't quite understand how you can get weight loss from particle pair production. I wish I had an answer for you on that, but jury's still out on that one. But just the fact that there may be overlap between Pogletnov's claims and Fouche's claims, because we are using superconductors with very high voltages that may be producing the Schwinger effect or the Pais effect. Another topic that you should probably be somewhat familiar with is called the Unruh effect. This is like the Doppler effect. If you are flying through space and you're accelerating through space, you're going to see all of the EM waves ahead of you compressed or blue shifted. You'll see all of the EM waves behind you stretched or red shifted. What this means, though, is that these relativistic plasma mirrors that I was talking about, they're going to be producing very high Unruh temperatures. And you can see here, this was one of the papers I came across. They were saying that if you use a stupid powerful laser colliding with an electron, it's going to produce 1,000 Kelvin of Unruh temperature as noted by that electron, which if we have a superconductor, this is a problem. Moving on, here is an antimatter drive that was worked on by NASA for a while, or an arm of NASA. It's called Project Icarus. It was a spin-off off of Project Daedalus, which took place from 74 to 78. Icarus was from 09 to 2019. This was just research-based. They didn't actually do experiments with this. They only utilized the experiments that had already been done and took the data from that. But they came up with a model for an interstellar craft that was using the Schwinger mechanism to create these antimatter particles that you need to be able to get the amount of energy that you need. If there's aliens out there, or if there's other intelligences out there, antimatter makes the most sense, because bang for your buck, you get the highest conversion of matter to energy when you have antimatter annihilation. According to Project Icarus, though, they were suggesting that you're only going to get somewhere around 1,000 positrons, or 1,000 particle pairs per MeV, which is nowhere near enough to be able to actually see any of the effects. You're going to need many, many orders of magnitude more particle production per energy input than what these very smart people from NASA determined. Coming back to Friedrich Winterberg, he talks about this, saying that you can have an antimatter plasma, or matter antimatter plasma. He calls it an ambiplasma, and that when it collapses, he's big into Z-pinch type fusion things, so makes sense where he's coming from. If you have an ambiplasma pinch, that you're going to get much higher rates of production of the antimatter. I wish that Dr. Winterberg would have worked with these NASA folks, because I'm sure they could have come up with even better models for a antimatter spaceship. So when you have antimatter particles colliding, they tend to give off gamma rays. This can be described by the Bright-Wheeler process. Although in the Bright-Wheeler process, you have multiple gamma ray photons that collide in the regular Bright-Wheeler process, and they end up creating matter from light. In the nonlinear Bright-Wheeler process, though, which is the lower right image there, you have a single gamma ray photon that is just in a very strong electromagnetic laser field, like the Schwinger effect. And that is how you're getting the antimatter production. In fact, there is strong overlap between the nonlinear Bright-Wheeler effect and the dynamic Schwinger effect. So speaking of these gamma rays, though, that are going to be produced from this, I started looking through the literature and the accounts to see, well, have UFOs ever produced gamma rays? And it turns out they have a documentary that just came out like a week or two ago from a team called UAPX. They ended up getting a lot of really good data. They set up a bunch of cameras and sensors on top of a rooftop down by Catalina Island, California. They had multiple locations so they could try to triangulate any of the UFOs that they spotted. In one of the encounters, they had triple repeating gamma ray emissions that were far above the background gamma ray emissions. Background tend to be about 2 MeV. Their average was around 10 MeV gamma rays. And the fact that they were triple repeating was extremely interesting. More interesting was the fact that they had their largest spike, which was 43 MeV, from a thing that was a couple miles away. So it stupid high energy densities that are coming from gamma ray emissions. And as far as we understand, in order to get gamma rays, you got to have either antimatter annihilation, or you got to have lasers that are far beyond what can really be produced right now. Getting close to the end here, we got a Feynman diagram for anyone who hasn't seen one before. I got the following slide. You're gonna have to be able to read it. So you can see the arrow indicates time as we're moving through time. Orthogonal to the arrow would be the space dimension. So you can see on the left-hand side, we have an electron and a gamma ray that are coming together. And then when they collide, that electron now is going to have a lot more energy such that it can't hold on to that energy, and eventually it's going to emit another gamma ray, and that's going to deflect it. That particular example that you see before you is Compton scattering, which was briefly described by the previous speaker. So here I've been mentioning the Bright-Wheeler process. If you look in the lower right-hand side, you can see the Feynman diagram for that, although it is rotated. Starting from the top and moving down to the bottom is our time direction. So you can see we have a gamma ray coming in with an electron. They come together, and then the electron spits off and it produces another gamma ray. Although what's not shown in this is that it's actually producing positrons, and that it is the mirror image of Dirac annihilation, which is quite useful in much of this research. All right, so bringing it all together. If you take a petawatt level, super fast femtosecond laser and you shoot it through a special film to produce plasmas, you can then focus that plasma, give it a curvature to produce a plasma mirror, which can reflect another laser beam being bounced off it and upscale that laser beam even further. So we can get very, very high energy densities, maybe even to the level to attain the Schwinger effect. And the fact that these are altering the refractive index of the vacuum blows my mind that this was even figured out, and especially figured out 70 plus years ago. Especially because once you're changing the birefringent value of the vacuum, certain non-linearities start taking over. The vacuum changes in extremely useful ways. Instead of being a linear change in the amount of particles produced or effects noticed, you start getting an exponential increase. An avalanche of this starts occurring above the Schwinger limit. Further, if you want to attain it, you're going to probably have to be using superconductors, which is very useful because that's what falls in line with everything else that we've heard thus far from Fouche or other sources. Alternatively, the nonlinear Bright-Wheeler or the dynamic Schwinger effect may be actually damping EM waves because of the ambi plasma described by Gunterberg. This damping of EM waves may also fall in line with some accounts of UFO or UAP data collection. Hard to determine. One of the most interesting things about this, though, is that the Bright-Wheeler process may not have normally rated decaying magnetic fields. It may have a much slower decaying magnetic field. And I cannot recommend watching this video link that I have here enough. This is a young guy who's working over at Brookhaven, who gave a talk down in Brazil. And he determined that we can get up to 10,000 times stronger magnetic fields from the bright Wheeler process than are even noticed by magnetars, which are already the strongest magnetic sources known in the universe. Also, these extremely strong magnetic fields has a touch of overlap in tone with the magnetic field disruptor technology described by Fouche of the TR-3B. So trying to identify, why it's all secret, aside from the fact that it's, next level tech. If they were using nuclear pumped lasers, nukes are illegal in space or in the air. Also, if they were using small modular nuclear reactors, those also are illegal, especially if these things are still flying to this day. Really hard for Uncle Sam to come out and say, oh yeah, by the way, we got this cool tech that we may have been flying over everybody's houses, producing gamma rays and causing potential for massive nuclear fallout should any of these crash. It makes sense why they would have to keep this secret, not just from a technological standpoint, but also from a public safety standpoint and from an international diplomatic relations standpoint. Also, because of the flight capabilities claimed of this craft, if they're able to deter nukes that are being shot off, this is something that you would want to relay to your enemies, but you wouldn't want to relay in such a way that they can figure out exactly what your tech is. You want to talk about the capabilities, but you don't want to talk about the way that you're getting these capabilities. So you have to reduce the amount of info that you give and only give enough info so that they know you can, not how you can. Also, these may have been developed in response to UAPs that would have been hounding us for, since time immemorial. Hey, finally, we got a way we can actually chase these things. That would also make sense why it would have to remain a secret, because it's part of the program, right? It's part of the UFO secrecy world. So if you come out with this thing and you say, oh, by the way, we've been chasing UFOs with this, once again, big can of worms. Just so many aspects of this require secrecy that makes sense. Not to mention that if they're producing these extremely high gamma rays, that is a potential for weaponization that you most certainly do not want any enemies to be able to identify. There's still a lot of questions, though. In the official commercial academic world, we're still not there even today, 30, 40 years after the fact, for the amounts of energy densities and laser energies and speeds of the lasers, all of the metrics required to attain this. We aren't there yet. And you're supposed to believe that 40 years ago, a group with unlimited resources and brains managed to be able to attain this. It's a slight leap in more than a slight leap in faith. Alternatively, there may yet be different methods for curved relativistic mirrors, those plasma mirrors. There might be different methods that they're using to produce these that we don't know about. There might be a completely different grand unified theory that they're working with to be able to produce these things. I might be way off in left field because it turns out they have a totally different model of the universe, which allows attaining these Schwinger limits to be even more attainable. As just one bit of evidence, though, to try to help the faith that maybe this has been possible, that they've possessed technologies for 40 plus years that we still can't even begin to imagine today. DARPA is regularly 20 years plus ahead of the curve on all technologies. By the time you find out about technology that has been produced from any government contract, generally speaking, rule of thumb, it has been researched and produced for a minimum of 20 years. So suggesting that the most secretive project in all of the Black projects was at least 40 years ahead of development. Maybe not so unbelievable. Just as a further aside to that, Ed Fouche talked about when he was working at Area 51, he was working on their satellite tech and their satellite receivers, and he claimed that in 1979, he saw FPGA processors, which weren't a thing yet. He saw these things the size of a Zippo lighter on the satellites, and that these processors were operating at about a gigahertz in 1979, when the fastest normal processor out there was, you know, barely even getting into the megahertz range. So it's possible. It's possible that there's faster tech, better tech out there that we just haven't got to yet. Wrapping it all up, maybe the TR-3B is using plasma mirrors, or maybe it's using negative effective mass from plasma oscillations. Just a lot of conjecture remains. So I have a Google Doc here with a link down at the end. There's a lot more that I haven't even begun to touch on potential avenues that it could be utilizing. I tried to condense it into just a few here, and even this was not very condensed. And now I'll just leave each of these links slides up for a few seconds so that anybody watching this as a recording that doesn't have access to these links can just type them in. The green ones are the ones that I highly recommend people go take a look at. That's what I got.
Man, Jarod, that was wonderful. In fact, there are people in chat texting me going, this is amazing. This is so much more than we thought he would present. So thank you so much. So in terms of this document, you have a ton of resources. If you're able, I mean, you can just email it to me if you want. I will put a link up to this in the replay, right? And that way everybody can see this. Since it's a Google Doc, just make sure to share a read-only link, right? And that way, you know, nothing happens to it. Nobody accidentally changes anything. But yeah, if you have a link to share, I'm happy to put this up in the meeting notes. You can also share that link in chat also. But before I do anything else, though, what I want to do is I want to stop your screen sharing, and we need to give you an applause. Everyone, tremendous applause for Mr. Jarod Yates. Jarod, thank you. Thank you. That was, yeah, incredibly detailed. And I love the fact that you did synthesis on so many different sources and you cross-referenced so many different things as well. That really makes it amazing.
I've just posted in the chat to the link to the Google Doc for anybody that wants it.
Oh, wonderful. Okay, and you know what I am going to do here is I will pop that open. And
also, the very last link on that links slide is also the link to the Google Doc. So anybody that is watching this as a recording, that you can type in that stupid long address and get to it there if it's not already in the description of the video.
Perfect. I got that as well. And let me see it. Yeah, no, it looks like it's not editable, which is good. We don't want to. Yeah. Okay. Perfect. Okay, well, so again, thank you very much. Let's go into Q&A session. The first person that we have Mark Sokol with the world's biggest grin, and he has none other than Mr. Travis Walton with him. So, Mark, go for it, sir. Oh, you're muted. Sorry. Let me.
Okay, there we go. Yes, Travis had a couple questions for you.
I've got a million questions, but a simple one would be, would the properties of these drives operating this craft interfere in any way with its ability to orient or communicate from outside sources, you know, things as far as where, you know, navigation and communication.
Absolutely. So yeah, in order to produce magnetic fields that are on the order of 10 to the 15 Tesla or some retarded high amount, you're going to have a lot of shielding in place. Not to mention if you're using nuclear reactors or if you're using tokamak plasma type containers, the amount of interference is going to be beyond ridiculously high. And how they would manage to shield against all that, my best guess would be utilizing metamaterials to be able to capture a lot of this. The fact that we see cloaking on a lot of these things as well suggests that they're able to redirect electromagnetic fields in ways that they want, which gives me hope that if this thing has been in play for as long as it has, and if we see these craft flying in formation like we did at the beginning of the talk, that there is ways for them to communicate, as well as have other sensors be able to be working while this craft is flying. I couldn't imagine any pilot flying one of these craft without having his whole instrument panel, not working. That just wouldn't make any sense to me.
Well, that was immediately comes to mind with the properties of the drive versus the need to orient yourself and navigate.
Also, as a further aside, some of the accounts of folks from the UFO community usually suggest that the reason why a lot of these pilots and these occupants of these crafts aren't just, turned into jello on the side of the wall when it accelerates at 100 Gs is they're actually weightless inside. That when they are generating these fields that somehow nullify gravity or somehow produce an anti-inertial effect, that the occupants inside are feeling nothing. The accounts specifically with the TR-3B suggest that there was an 89% reduction in the amount of inertia felt by the pilots. So accelerating at 100 Gs means they were feeling 8.9 Gs, which the average pilot can only handle 8.9 Gs for like a second. But a second is long enough to go from 100 feet to 100,000 feet when you're accelerating at these rates.
Is there any way this craft could be piloted without human beings inside? Could be operated in some way, programmed to go to a particular point?
Absolutely. So yeah, we already have plenty of good examples out there of UAVs, unmanned aerial vehicles, right? That we've had these things for 30 plus years, 40, 50 years, where these things fly on their own. They don't even need a remote pilot. They can just be given a certain set of commands and they're able to follow those commands. For the longest time when researching this, I was suspecting that if they were having trouble getting the inertia aspect of the whole package down, they would have been having to fly them either remotely or automated. But
from killing the pilots.
Yep. But based off of a lot of the flight patterns that we've seen from these things, it would suggest that they are under some form of active control, not just a passive or automated system. But there's actual pilots that are able to deal with greater unknowns and thus react in a faster time frame.
So they've achieved inertial isolation or
reduction
at least.
Travis, in your case, did you ever feel weightless on board the spaceship?
Actually, I felt heavier, but that may have just been because I was injured. I could hardly move my body.
If they do have control over the gravity inside or the inertial one fields inside, it would make sense to make it comfortable for whoever is inside, right? They wouldn't necessarily make you weightless if you need to be able to, get to certain panels or move around in a way that you're more used to. If you're feeling an extra amount of added weight, that may be because the inertial effects are working overtime and they're still not fully overcoming the accelerations that the craft are undergoing. It's all conjecture.
Live on a very large planet and need 1.5 G in order to be.
Mm-hmm.
to keep their timber.
The external dimensions are enormous. I'm curious about how much of the interior would be just, drive equipment, and how much of it would be open to, cargo or passenger space.
So from the research I've done of it, it suggests there's usually 4 occupants, a pilot, a nuclear specialist for the reactor, usually a co-pilot who is also doubling as the electronic warfare, the backseat guy, and then a 4th person who is usually rotating either as someone that they're taking somewhere, or if they are doing certain special activities, they may need more hands on deck, so to speak. But 4 has been, generally speaking, the maximum I've heard, just because they're already barely overcoming all of the forces necessary to even achieve flight. So it does not have a huge payload capacity, even though the thing probably weighs somewhere around 60 to 200 tons. It's using all of that mass to negate a lot of its mass.
Well, the deceleration I witnessed would have been crushing without inertial isolation.
Okay, Bruce Cornett.
What wonderful. Yeah, sorry about that. Okay, well, Travis, thank you, sir. So let me go to Bruce Cornett then. Bruce, go for it.
Yes, I just wanted to mention that I put a link to my video in the chat to a video of the TR-3B that we captured on the 10th of May 1997. I mean, yeah. Anyway, it was 1997 when we got it. There were 3 of us with 3 cameras, and we were told later that we'd got permission from the Pentagon for Skunk Works to give us a demonstration. So if Jarod wants to take a look at this, I'd love to have his comments, because this triangle does all sorts of amazing maneuvers in the night sky.
Bruce, I would love to see that video. I'm not seeing it in chat at the moment, though.
It was early on that I put it. So
Yeah, I think let me see. Here it is. So that's the bufo.co.uk, I think.
Right.
Yeah, I will. Let me see if I can repaste that in there. Nope. No, it's not working.
Try at my end here.
Okay, I see it now.
There, I just repasted that in the chat as well.
Okay, here it is again from my end. Anyway, that's really what I wanted to say, other than that this is more information that I've seen about the TR-3B than has been released by anybody, and that's phenomenal. Thank you.
Thank you
and thank you as well, Bruce. So again, and oops, where'd my file go? So if you want to raise your hand at Zoom and ask questions, it's Option Y on Mac or Alt Y on Windows. And again, Jarod has done a tremendous amount of research on the TR-3B, and Jarod, I can't thank you enough. It's putting the pieces together. It's the synthesis. That's what excites me.
Mm-hmm.
It's and then researching, I guess, these. What would you call it? Convergence of technologies from different sources. That's also incredibly intriguing. So
one of the things that I'd like to mention is that Ellen Crystal photographed triangular craft back in 1980, before the flap that occurred in the Hudson Valley, and she puts those pictures in her book. And what is interesting about them, she was claiming that these were, ETVs, but I'm beginning to wonder whether or not they were early models of the TR-3B, because they give off so much radiation that is being picked up by the film on the camera. And that may have been some of the first evidence that they were out flying around in New York.
Yep. also further, I didn't talk about it, but one of those earliest images I showed at the beginning of the green night vision looking triangle, those were the images taken by all of the Navy personnel on a carrier or destroyer, just like in the last couple of years. And the debunker community got all over this saying, oh, those are just a camera artifact of the night vision. They were calling them bokeh triangles. I strongly suspect that there has been interactions between these craft and our military personnel. Supposedly the craft are not under the control of the military. These are private enterprises, Lockheed and potentially Boeing, that are owners of this material. So that's one way that they're able to prevent the general public or even government officials from getting their hands on this stuff and thus disclosing it, is by keeping it in the commercial sector, where NDAs and protection of information is actually easier than when you have required oversights from military officials and others like that. Yeah, there's been so many sightings of these things throughout the decades, and it's possible some of the triangles out there aren't ours. It's possible all of the triangles out there aren't ours, that the TR-3B was a big disinformation campaign. I'm not going to say one way or another that this thing actually exists or that it doesn't exist. But from the evidence of what I've researched, it suggests to me that the potential for its existence is there.
Awesome. Awesome. So again, oops, sorry about that. Just somebody else come in. Yeah, so Option Y on Mac or Alt Y on Windows, if you want to ask Jarod a question. And Jarod, you've covered so much territory. I think that might be part of the challenge, is that, you know, we've got a lot of blown minds in the audience. But
it was a lot of information and a lot of material, and it's like you have to have a combination of ADD and OCD to be able to capture all of these extremely disparate ideas and yet be able to dive down into each one of them to be able to identify any overlaps between any of them. It is not a simple task to listen to this, let alone to try to research this.
The overlaps are what's exciting, though. And you know what it reminded me of? Maybe this sounds cheesy, but Jeremy Reese, right, who's here today, sort of kind of, he used to do these videos years ago, right?
Yep.
And so your presentation kind of reminded me of his videos, where Jeremy would it was this synthesis that made it greater than the sum of its parts. And so that, you know, again, that's the exciting part.
I cannot shout out to Jeremy enough. Honestly, his work on this, I felt, was as groundbreaking as Ed Fouche's. Ed Fouche gave us the information. Jeremy gave us some synthesis of it, as well as exposure. His video going viral exposed the world. So many millions of people all of a sudden went from never having heard about this to finding this, you know, plausible and interesting. So big thanks to Jeremy for everything he's already provided on this topic. Huge thanks.
Yeah, he's done so much on it. He's done so much. Okay, well, let me see. Michael Boyd has a question. Michael, go for it, sir.
So I'm curious about, one of the things you didn't talk about was different mediums. Like we've seen the UAPs are under the water as well. So I'm curious about your thoughts on that.
So my research on this is ongoing. Some of this information I just came across even last night and added to the talk. Like it's my biggest passion next to the Grab-a-Flyer. All of my free time goes into researching warp drives, and usually with a gear towards either the Tic Tacs, as Charles Hall described, or the flying triangles. With regards to the Tic Tacs and their ability to do transmedium travel, a book I just came across last night from 2014 by some NASA guy, he goes through and he analyzes all the data that we have, especially he gets some mass measurements and calculations from imprints in soil from some of the craft. And he suggests anywhere from 25 to 60 tons as a weight of these things. But he also suggests that their mass density is similar to water, that it's like 94, 96% similar to water. And that's part of the reason why they're able to do the transmedium travel. They're actually like flying submarines, which having that much mass and being able to fly is mind blowing. But for the transmedium travel for the TR-3B, the skin of the craft is likely to possess a lot of electronic warfare protections, right? So just like the F-117 or other F-22 or any of the stealth aircraft out there, they have normally radar reflecting material. In addition to that, now we're starting to see that because of the left-hand metamaterials, they're getting camouflaging abilities of this as well. They're able to redirect the light rays around them. In order to actually do transmedium travel, though, in a way that doesn't destroy the aircraft, you have to be, that warp bubble around the thing has to actually like extend far enough, or you have to have a shielding of some kind. Shielding was one thing that I didn't mention that may also be responsible for the gamma rays observed. If they have electromagnetic shields around them, that may present a route or a method for these gamma rays to be emitted. Also, there's plenty of accounts out there of people who have approached UFOs and they get ionizing radiation burns, right? This is all over all the UAP reports. I just came across one incident from 1960 something where a couple of guys from Central or South America, they got within 20 feet of a craft, and in 2 days, one of them had died from the gamma radiation that liquefied his inside.
Travis over here got hit by a lightning beam when he approached the craft.
Pleasure again, Travis. Take care. Have a safe trip back.
Yeah, actually, Travis, could you describe a little bit the size, the shape, the color, and the distance from you to the craft of that beam?
It was instantaneous. It was a flash. It was something that the rest of the crew described as blinding. One crewman was interviewed by an officer and described it as looking like a long blue flame. Another described it as a foot-wide beam, and another, compared it to a bolt of lightning. So they all have their different interpretations of what they saw, but there was also just the idea that it was blindingly bright.
Excellent.
That bright, it's hard to see any color.
They all bluish green, greenish blue.
The color is important, but also the shape is important, right? If it was a smooth beam versus a jagged beam like lightning, that may indicate different mechanisms at play. If it's a jagged beam, it's probably like electrons, right? It's conducting electricity down. But if it's a straight beam, that means it's using photons, and photons aren't going to be doing all this ionizing branching effects, which if we're trying to reverse engineer this, or even at a bare minimum, understand this, identifying all the characteristics of these effects that we see come from the craft is extremely important.
Did you get a sunburn?
I didn't, but
did you get any physical effects like heating your skin, or did you feel hot?
A faint heat on my bare skin, my face looking up.
Because protons, a proton beam wouldn't penetrate. Protons don't go very far. Alpha particles, but beta, they go a little bit farther, but gammas go all the way through. So you wouldn't feel the gamma, but you would feel the alphas. You follow? Because they're like
the crewman that was exposed in the truck developed skin cancer on his bare arm.
Oh.
Was that the arm that was like out of the truck?
Yeah, it was towards on the side towards the craft.
Gotcha. So yeah, he got a radiation burn.
How long after his exposure did he develop the cancer?
It was a number of years, but he was a very pale, fair-skinned individual.
And approximately, what would you guess was his distance from the craft?
At least 90 feet, probably.
You were closer.
Yeah, I was closer myself.
But he was.
So was the craft aloft, or was it on the ground?
It was aloft.
So now the fields are the anti-gravitational fields are going to be producing themselves are going to be producing radiation because it's blue shifting. That's what's causing the space-time there is expanded compared to normal space-time, let us say. So that's going to cause Hal Puthoff's did a couple of videos where he's talking about the harmful effects of this technology. He has one about where he talks about blue shifting and how you can get radiation burns if you get too close to these things. So I appreciate your answers and thanks.
Thank you.
Yeah, thank you for your insights, Travis.
Yeah, wonderful, wonderful. So let me go back to Bruce briefly.
Oh, two
Bruce,
things I wanted to mention. Number one, in that triangle demonstration, which I think is the TR-3B, as it approached the cameras, there were two camcorders and one SLR. It shut down my Mark's camcorder. He said, my battery's going dead. I just charged it, and mine wasn't affected. But then the craft increased the intensity of one of its lateral lights to almost the brightness of the moon, and it started producing what does he call it? Lens flares in my camera. You could see that as well. And the other thing, mentioning cancer, is that Ellen Crystal in her book describes getting very close to one of these triangular craft that was hovering right on top of her. She close enough that she tried to jump up and touch it. And she unfortunately died of pancreatic cancer 10 or more years later. So
awesome. Okay. Well, thank you, Bruce.
So just an observation also about that. There was a guy by the name of Bill Uhouse who hung around Area 51 and the ALE Inn for a long time. And he told people that he had worked out at Area 51 in the 50s as a flight simulator instructor for the craft. He claimed that the craft were using somewhere in the range of 6 million volts to actually attain an electrogravitic effect for their levitation, and that they could only operate for about 30 minutes because of the amount of liquid nitrogen that they had on board. And that when he was inside the thing, he had to wear like chainmail type thing and move very slowly so as not to arc because there's such a high electrostatic potential inside that thing. One other thing that I want to mention is that a Tear in the Sky documentary that I just saw, where the team of scientists took all of these instruments onto a rooftop down by Catalina Island. That 43 MeV gamma ray that they observed, 3 minutes prior to observing that, they had 8 FLIR infrared cameras pointed all over the sky, and 2 of these cameras were actually oriented in a way where they would have captured this thing. And just a few minutes before it emitted that energy burst, all 8 FLIRs went offline at the same time, and they were powered by 2 separate power sources, and they still all went offline at the same time. So to me, that sounds like one of 2 things. One, either they are just overloading the circuitry in it, which I don't think is necessarily the case unless it's a very directed beam. Or 2, they might have inside information on different tech that we have, and they're using that information to specifically target certain tech that we have. So if they got all the blueprints and the schematics and the diagrams for FLIR cameras, hey, now we know exactly how to, pop these offline, just like a 0-day hack for any software-based type interference. So their electronic warfare capabilities, either they have very good directionality, or more likely they have superior knowledge or insider knowledge of some of our tech.
Yeah, Josh, sorry, Jarod, are you talking about UAP or with the TR-3B? Because with the Catalina Island, it's UAP, right?
Correct. Although they did have one capture of a triangle. I don't think the triangle was the one that was where they were detecting these very high gamma rays from. I think they still detected some gamma rays from it, but they didn't go into it. I've reached out to some of the scientists from it. I haven't heard back from them yet. I'm trying to get their data set. That would be amazing. Yeah, so you just have to, choose how much skepticism or how much belief you're willing to have. If the TR-3B is solely human tech, if there is no alien tech, if the only thing out there that we see is human-based tech, which I don't believe to be the case, then that would give one avenue for how they would have insider knowledge, because of course they're going to reverse engineer, the FLIR cameras that they already have on board. Of course, they already have contracts with FLIR to have full access to all of their engineering diagrams. However, if you take the superior intelligence model, even a moderately superior AI would be able to very rapidly identify certain components of certain tech and be able to identify how to overwhelm that tech in a way as to render it useless.
Well, yeah, and if I could suggest something, and I'm sure this wouldn't be universal, but so I guess there are a couple of thoughts. One of them is, as our technology continues to progress and develop, right? Microprocessors become more, we call it, the chip sizes become more fine, and so it's going to be easier and easier and easier to knock those offline with electrostatic charges, or you name it, any kind of energy, whether or not it's directed, right? And that's just because we don't shield things as much as we could or should. Things aren't necessarily radiation hardened, but those transistors inside of our chips are just getting smaller and smaller. So part of it could be that. The other part, and this is something that I personally feel, is UAP, if it's intelligently controlled, and I personally believe it's machine intelligence. That's just kind of my gut feeling. Back in with Travis Walton's encounter, that was back in the days of, I don't know what you call it, the real world, I guess. Now, everything we have is online, and so they wouldn't necessarily have to identify components. They could just look up the schematic for the model number, and that's just something that I kind of assume is a given. If positing that UAP are real and they're intelligently controlled by somewhere, I would just assume that they probably know everything we have. They could be, not to sound paranoid, they could be watching this right now, chuckling, So
one of the analyses I saw on a supposition on how their information systems may work, they could have exaflop or higher computing power. In like a small cube, they could have the amount of computing power of the entire planet, right? Which means that it's not that big of a stretch, if they have that, to say that they're able to very rapidly identify weaknesses of any of our abilities to track them or to identify characteristics of them.
Yeah, I would tend to agree with that. I mean, the capabilities of those craft, just in general, seem to indicate incredibly high amounts of just information processing, right? And I mean, when you look at computers, really for us, computing is probably about 50 years old, the way that we think of it now. You give that another few hundred years, and where would that be? So, well, let me see. Does anyone else have questions for Jarod? Jarod, if you want to come back and do a presentation on UAPs, if you want to do something like this for UAPs, oh, please, please.
I would thoroughly enjoy that.
I have. Sorry, jump in. I have a question. Do you think that they combine all our telecommunication, all the impulses of electrical communication that we have, and they harness it into 3 points of existing? I mean, that would only logic be, the resonance of all that energy that we're emitting. They have to be able to harness it somehow, and use it to materialize a space and time to take an image, like, of where we are as a civilization, and, make it smaller and smaller, and somewhere, they stack it as a time image of, our energy level. I mean,
Absolutely, absolutely.
Look at a shape, even. It feels like it's like a place where they store timelines, and then it goes off somewhere and it gets put, on a bigger scale of a stack and so forth. But we might be able to, imagine that image or that shape with those dimensions, apart from a more gigantic structure.
Yep. So I think one of the most useful things in trying to research or understand anything that is above your pay grade, which is definitely above my pay grade, is trying to maintain a certain amount of awareness of you don't know what you don't know and how much you don't know. So if we take that to, who knows if it's even the extreme, for more intelligent things out there or more capable things out there than us that have been around for potentially a ridiculously much longer time frame than us, they may already have all of the potential advancement trajectories for a civilization as it grows, right? And so for them to come in to a backwater place like here and say, oh, look, they're at this stage, let's just do a quick snap. Okay, now we got all of the information on that entire planet. Let's analyze it. Wait 2 seconds. Okay, now we totally know where they're going, what they're doing. They would already know everything about it. It would be a walk in the park for them.
Yeah. Well, so on that note, let me, Mark is ready to go. So let's do this.
Thank you.
Let me, and thank you, Lulu. Let me put this back on gallery view. Everyone, please, another applause for Jarod. A wonderful, incredibly in-depth presentation. Jarod, I would love you to come back and do something similar on UAPs, if and when you're open to it.
Yeah.
And so what I'd like to do now is I want to go to Mr. Sokol. Mark, I'm going to spotlight you. Take it away, sir.
Okay, I'm going to make this really quick. So I'm here at MUFON, PA. Everyone's actually at dinner right now, so we'll have the place literally to ourselves. And this is just a one-night event here. So the conference is sort of winding down, but we're at the Sheraton, Bucks County. This was the main speaking hall. Over here, there was about 150 people in attendance. This is the first conference they've had since the pandemic. So it's been pretty exciting. Nick Pope, our very own, was here. Travis Walton was actually watching the conference and signed up, and he plans to attend APEC in the future. We have our APEC sign over here, and there's been quite a bit of interest. People are using the QR code on top, Tim, that you made, and are signing up for the conference. But Travis Walton actually was talking to me the whole time, asking questions about Jarod's presentation. He seems pretty knowledgeable. Over here on this, on our table, we have just some of the scientific papers. It's a great contrast to have, talking about lights in the sky in there, and over here we're talking about building those lights in the sky. Some people were very interested in this. We actually had a couple people who wanted to come down to the lab and took down my information, planned to come down for a tour and possibly working with us. And this, I'm going to be presenting this at APEC probably on a different event. But this is the gyroscope machine inspired by Mike Gamble. We have now 4-inch gyros, and we have them mounted at a slightly different angle. These are 90 degrees to what they were before. And these are much more powerful than in our past setup. And they swing back and forth using the same servo system we had before. So this we actually got this running at the lab earlier. It does inch along. It needs some fine tweaking still in order to finish up to get the maximum amount of thrust out of it. The presenters had their own little tables here. There was t-shirts and signs for sale. You can get posters from Travis Walton, signed posters as well. They had lots of t-shirts and stuff. They started putting all that stuff away because we are at the tail end of this conference right now. And there was a planetarium here as well. where you could learn about all the stars. That's pretty much what's happening here in Pennsylvania at MUFON, PA. And I'll catch you next time at the next APEC conference with further updates. Oh, Jarod.
Hey, yeah, I was just wondering, did you hear of any speakers there that really stood out to you? I mean, other than Travis or Mick, or any things?
There was one speaker that I was very excited to hear from, and he was actually the only one who didn't show, who was going to talk about UFOs and how they disrupt communication and electronics. And that presenter didn't show up. But most of the stuff that goes on at MUFON is lights in the sky. You know, a UFO landed over here. This is amazing. You know, we're finding radiation. So it's not really like as engineering as we are. They're more like, oh my God, they exist. This is amazing. We're like, yeah, they exist. Let's build them. So it's, I kind of feel like a little egotistical maybe, but yeah, we're like a little couple steps ahead.
Yeah, well, that makes sense. I mean, a lot of the traditional UFO community is very subjective, right? You know, and you know, we've cross-pollinated a lot more with the SCU, you know, and they are, you know, mostly PhD scientists. So
I mean, half the people at the SCU are people that come to APEC.
Yeah, and then we have a lot of, you know, and I see the guest list. I don't see all the I don't see all the chat windows
on where they are to each other, because they understand each other. I mean, most of the rest of the public don't. So they create these conferences where, you know, the rest of the public doesn't understand it, but they do, to show off, you know, or validate each other. Like, we're going in the right direction. You know, at the end of the
day, it's a feel-good sort of scenario. The other night, I was actually attending an AlienCon live event that had in Newark, New Jersey, with Nick Pope moderating, and George Yosukoulos couldn't make it because he finally got COVID, but he was there on the screen on Zoom. And Travis Taylor from Skinwalker Ranch actually made some very interesting revelations. He said that Skinwalker Ranch is a lot scarier than the TV show portrays, because a lot of the stuff that happens is not caught on camera. The camera crew don't stay the night. So there's a lot of stuff that happens that just there's no cameras. So, you know, they have to live it. It still happens. And then some guy, some heckler got up and was screaming at Travis, trying to find out what happened when they drilled at the end of the last season. They were drilling a hole, and that's where the season ended. And he couldn't take the cliffhanger from. They actually ended up pulling him out of there with armed guards. That was the highlight of the whole event.
That's right. You have to wait until the next season. You can't jump the gun like that. That's just not right.
Ed Travis is chuckling a little bit. Like, I think they probably found nothing, but you're not going to find that out till the next season.
Yeah.
I saw they were analyzing the data of like where their helicopter was, and you know they had it on some
they got radiation.
And then they found ones that they didn't create. They were just there.
He said they saw microwave radiation coming from all directions. It wasn't directional. There was radiation burns. There were people that ended up in the ER, and not everything was caught on camera because the cameras weren't always running.
Interesting. Well, so what, I mean, other than I guess what you call the validation, the subjectivism, what are some of the things that jumped out at you with MUFON this year?
Mostly the age of the people. It's they're mostly much older, and there is a lot of, you know, tapping yourself on the shoulder and saying, yeah, I was right. You know, because UFOs are moving into the mainstream. We have on Tuesday, there's the Congress is having a hearing on the stuff at 7 p.m. Eastern, talking about UFOs and UAP with the Undersecretary of the Navy giving their preliminary report. So there's a lot of that going on. Also, if anyone is in the area of New Jersey, on Sunday night, there's going to be a total lunar eclipse. This is visible throughout America, but we're going to be running the 3-body alignment experiment that Bob Greener talked about with looking at spectral lines. The strength of spectral analysis on different materials should be going up by 2 orders of magnitude during the lunar eclipse. Also, we're going to be casting different kinds of metals and looking at their crystalline structure. The crystalline structure during a 3-body alignment is supposed to change per Bob Greener's presentation that he gave at the last APEC. And we're going to be testing that this Sunday night on the 15th at around midnight at the lab. If you want to come by, if anyone's in the area of New Jersey, you're welcome to come by and have beer and some barbecue and, watch the eclipse through our 8-inch telescope and, hang out and watch the experiments unfold. I think Jeremy Reese plans to live stream that event as well. We might get Bob Greener on to talk about what's going on if he wakes up on time. That would be like 4:30 in the morning his time. So we'll see what happens.
Yeah, no, that's gonna be really interesting. And beer and barbecue. So
Yes.
yeah, it's the total package. It's the total package. There you go. Yeah, it is interesting. Well, Mark, thank you so much for going to MUFON. Thank you so much for coming live from it too. This is really exciting stuff. So we're the only conference that covers other conferences because we're kind of crazy.
We crash other conferences.
We crash other conferences. Yeah, I know.
Yeah.
Yeah. Well, did you have anything else to share, or should I go to?
Yeah, let's move on to the Alcubierre guy.
Okay. Yeah. Well, let me do that then. Hopefully, I can do this without botching everything. Okay. So let me do this. I'm gonna mute everybody out. Okay. And guys, I guess I'm gonna start this video here. Give me just a second. Okay. And I have to kind of move this so that it fits. Oops. Yeah. Okay. So now I'm going to share my screen. Okay. And let me see. Can you guys, I can see Michael in chat. Can you, or could you guys just type in chat? Can you see oops. Yeah, actually, you know what? Let me stop sharing for a second. I need to share that again. There we go. Okay. And yes, you can see my mouth is wide open. I will start playing that. And I guess, guys, just give me a thumbs up if you can hear the audio, and I will mute myself out. I'm Tim Ventura, and we're joined today by Dr. Miguel Alcubierre, who proposed the Alcubierre drive in 1994 paper as a theoretical solution to the field equations of general relativity to allow the creation of a Star Trek-type warp drive. Dr. Alcubierre is the director of the Nuclear Sciences Institute at UNAM and joins us today to discuss his vision for faster-than-light travel. So Miguel, welcome. Let me start by asking what your inspiration was to become a physicist back in the day, and what further inspired you to write the paper proposing your model for the Alcubierre drive.
Yes, of course. Well, my first inspiration to become a physicist was when I was around 14 or 15 years old. I actually liked a lot of astronomy. I started reading books about astronomy, everything I could get my hands on. I'm talking about the late 80s, so there was no internet. You had to go to the library to read about these things and find the books. It was not easy, but I read everything I could. And my dad actually, when I turned 15, he gave me as a present a small telescope, a 4-inch reflector telescope. So I would go out at night and look at the moon and the planets, Jupiter, Saturn, particularly Saturn is very beautiful when you see it, even with a small telescope. The rings are fantastic. So at that time, I started thinking about astronomy. I also started reading a lot of science fiction at the time. Essentially, initially Asimov and Arthur C. Clarke were my favorite authors at the time. So I read everything I could get my hands on from them. And Asimov was not only a science fiction writer, Asimov was also a popular science writer, and he was very good. He actually wrote excellent books about introductions to astronomy, for example. And I read that one, it was amazing, because he talked about how the ancient Greeks learned about the stars and the motions of the planets, and then all the way up to the mid 20th century, which is when he was writing these things. So I became in love with astronomy, and by the time I was 17, I decided I wanted to be a professional astronomer. So I started finding out what I had to do in order to become an astronomer. And I discovered something that I guess a lot of people that have the same idea eventually discovered. Astronomy is not actually a career in the sense that there's no course in university that is just astronomy. All astronomers are first physicists. So in order to become an astronomer, you first have to become a physicist. So I said, okay, then that's the way forward. I'll study physics. So I went to the local, it's actually the National University in Mexico, but since I live in Mexico City, it was close to home. Actually, it's in the same city. So I went to the National University in Mexico to become a physicist. And I studied there for 5 years. After during those years, I learned that most work in observational astronomy is not looking at beautiful things like planets and things like that. It's actually looking at things that I particularly found boring, which was measuring interstellar composition and things like that. So I didn't really like those things. I really was in love more with the theoretical sides. And I learned relativity when I was an undergrad student. And then I did a master's degree also at the National University in Mexico when I was about 23, 24 years old. And again, I took a course in relativity, in advanced general relativity when I was doing my master's degree. And I actually fell in love with the theory. I really liked the whole idea of general relativity, the whole idea that gravity is essentially just a manifestation of the geometry of space and time. I think that's one of the most elegant ideas in physics even today. And I fell in love with that. And I decided I was not going to be, after all, an observational astronomer. I was going to be more like a relativist, which is kind of an astrophysicist, but only sort of tangentially. I actually liked black holes and the Big Bang Theory, the origin of the universe, and those things, which is not quite astrophysics, or even less, because there was essentially no observational evidence for black holes. And even though we knew that the Big Bang was true, cosmology was actually only at its infancy, and we didn't have good data for cosmology even in the 80s. The data was very sparse. But I really liked the theory, so I decided this is what I'm going to do. I want to become a relativist and study general relativity, and I want to do a PhD in this subject. So I went to my professor in Mexico City, who had taught me he had given the course on advanced general relativity. And he told me, well, if you are interested in this, I actually did my PhD in Britain, and I have had a very good supervisor, Professor Werner Schutz. So maybe I can write to him, and maybe he can receive you. And he did, and Professor Schutz actually wrote back saying, yeah, he can come. He needs to get some money because I don't have money here. But if he can get a grant from Mexico, then he's welcome to come. So I went there. I went to the city of Cardiff in Britain. Cardiff is the main city in Wales. It's not England. Never actually tell a Welsh person that he's in England, because he won't talk to you again. I had to learn that again, because in Mexico we tend to group the whole of Britain into just England, which is of course wrong. And then I went to Wales, to Cardiff, and I did my PhD over there. I started working in something we call numerical relativity, which is the way in which you can write the equations, the field equations of general relativity, in a way that can be solved by a computer, with a computer program, because the equations are extremely complicated. So solving them with pen and paper is really hard unless you have extremely high degrees of symmetry, like a completely spherical and static black hole, then you can solve them. Or a completely uniform and homogeneous cosmological model, then you can solve them. But as soon as you add a little complication, it's impossible to solve them by hand. So you need to solve them on a computer. So that's what I started working on. And numerical relativity, particularly at the time, it was the early 90s. who were interested in modeling the collision of two black holes, because we thought, and it's turned out to be true, that the collision of two black holes was going to be the most important source of gravitational waves. Gravitational waves had not been detected then. They were detected for the first time in 2015, and I'm talking about the early 90s, so it was 25 years before the first detection. But we're already interested in this, and my supervisor, Professor Schutz, was interested both in the numerical modeling of these systems and also in the detection of gravitational waves. He's one of the pioneers in the detection of gravitational waves. But even though he had students doing both kinds of things, my own work was more in the direction of this solution, this numerical solution of the collision of two black holes. And I worked on that for many years, the whole 90s actually. But while I was there, while I was in Cardiff, I'm also a fan of science fiction, as I mentioned earlier. I used to read everything I could get my hands on in science fiction. I also used to watch TV shows and movies about science fiction subjects. So I always liked Star Trek. Even when I was very young, we could see the original Star Trek series in Mexico on the TV. So I always liked it. And when I was in Cardiff, we were watching the Next Generation series, the one that started in the late 80s and early 90s. So I would used to watch that show with my friends. The other students, the other PhD students that were doing their PhD over there, they all loved Star Trek. So we used to get together on the Friday evenings to watch Star Trek. We would rent, it wasn't even a DVD, it was actually a VHS tape of Star Trek episodes, and we would watch it together. And one night when we were watching Star Trek, I started thinking about that, because they always think, in Star Trek, they always talk about moving faster than light, and they talk about something they always call the warp drive. The warp drive is a name that actually comes from science fiction. And it gives you the idea that warping is curving and it's deforming things. So it gives you the idea that if you want to travel faster than light, you need to deform space somehow. Because in relativity, traveling faster than light normally through space is not allowed. Nothing can travel faster than light.
Yeah.
So I started thinking about, well, if they talk about distorting, warping space to travel faster than light, they never say how it's actually done, because it's just science fiction. So maybe there's a way to actually deform space that will allow you to travel faster than light. And I started thinking about this. I'm doing a PhD in general relativity. In general relativity, it tells you that gravity is a distortion of the geometry of space. It's a warping of space. So maybe there's a way to use gravity to warp space in such a way that it allows you to travel faster than light. There was already an idea about doing this that had been many decades old at the time, which was using something called wormholes, which is a sort of tunnel through space-time. You make a hole in one place and it comes out somewhere else. This is actually allowed in general relativity. It's very surprising, but it's allowed. But nobody knows how to make one. And it's actually complicated, because you need to punch a hole through space, and we have no idea how to do that. Even if in principle the theory allows you to do it, in practice we have no idea how to do it. But I came up with a different idea. I said, well, maybe instead of punching holes through space, do something else entirely. At the time, I was also studying a little bit about cosmology. And cosmology, which is the study of the evolution of the universe, you learn very early on that the universe is expanding. We've known that for about 100 years now, that about the expansion of the universe. And the expansion of the universe was detected observationally, because the galaxies move away from you the further away they are. But it was predicted theoretically before it was even observed. It was predicted in the mid-20s of last century. And it was predicted using the theory of Einstein's general relativity. Sorry, it was predicted by that theory. Einstein himself didn't predict it. I mean, he actually found that space couldn't remain static in a cosmological setting, and he didn't like it, so he invented something he called the cosmological constant to stop this from happening. But other people actually didn't like this idea of Einstein and explored the possibility of having a space that was expanding. So this actually a scientist called what was his name? I forget it at this time. It's terrible with name. Lemaitre, George Lemaitre. He was a Belgian physicist, and he explored this idea of having an expanding space. And he actually thought that if space was expanding today, back in the far past, it was concentrated in a very small region, which he called the cosmic egg, which is the first impression of what the Big Bang that we have today. So he didn't call it the Big Bang, he called it cosmic. But we have this idea that space is expanding. And the expansion of space is very interesting because people tend to think that that's because there was some big explosion here and everything is just flying apart. That's not what happened. That's not the Big Bang. The Big Bang was the origin of space. There was no space, and space sort of started expanding everywhere at the same time. And the galaxies are not so much moving away from each other through space. They're essentially sitting there very quietly in their own corner of space, but space in the middle is expanding. Space is stretching. It's space the one that's doing the motion. It's not so much the galaxies. So space can stretch, and it can also contract. And we also had this idea in the 80s, something called inflation, which is the idea that in the origin of the universe, in the very, very early universe, the very first fractions of a second, the universe expanded very violently, exponentially. And this expansion meant that things that were very close together suddenly moved away from each other faster than the speed of light and were no longer in causal contact. They couldn't influence anymore each other. And this was invented to explain the fact that you can see when you look at completely different directions in space, everything looks exactly the same. And if you look at the background radiation of space, it looks exactly the same in different directions. And that didn't make any sense because these regions of space in an expanding universe have never been in contact. And if they've never been in contact, how are they so alike? So that this idea of inflation was invented to explain that. But that meant that you could actually expand space faster than light. And this doesn't actually violate any laws of physics. So I was thinking about these ideas, and then I said, well, maybe if you can expand space behind you very violently, like in the inflationary theory, then you will move away from whatever's behind you faster than light. And that's allowed in the theory because it's space itself, the one that is expanding. But very quickly, I realized that this doesn't help you because you want to get closer to the things that are in front of you, not so much away from the ones that are behind. So I said, well, maybe you can contract space in front of you, which is, again, allowed. It's an opposite expansion. I said, well, combine both ideas. Maybe you can expand space behind you very violently, and in a completely symmetric way, contract space in front of you, and that will push you away from whatever's behind you and pull you towards whatever's in front of you, and you can do this faster than light. So that was the basic idea. It actually occurred to me in a half an hour or an hour after watching Star Trek on a Friday evening. And then next day in the morning, I went very early to the university. It was about 7 a.m. I was already there doing calculations, and I was using this computer package that allows you to manipulate Einstein's equations algebraically, not so much numerically, but it allows you to do calculations very quickly that would take you forever by hand. And after a couple of hours, I came up with a little set of equations that allowed you to actually have this kind of expansion and contraction behind you. And then I refined the ideas that allowed you to actually weeks and have this, and that's how the work product idea was born. I eventually went to my supervisor, and then I refined the ideas that allowed you to actually weeks, and I said, I've done this. I was afraid because I thought he was going to tell me, this is crazy, forget about it, and keep doing the black hole collision stuff that I told you, right? But no, he was actually very enthusiastic. He liked it a lot. He read it and he said, "This is really nice, Miguel. So you should actually publish it." I had at the time I've never published a scientific paper. I was just doing my PhD. I was just a student. So he said, "I will help you to draft a paper." So he helped me with the basic ideas. I drafted this paper, and then when I took it to him, the title was boring. It said hyperfast travel in general relativity. That was the title. And he said, "No, Miguel, that's not going to sell the idea. You have to put warp drive on the title." So I did. And that's the new title was the warp drive. And then the other thing was just the subtitle. And I sent it to a scientific journal. It was published in 1994. So that's essentially the history about the warp drive, how I got the idea.
Yeah, well, I mean, there are so many things that are absolutely remarkable about this. You'd mentioned Asimov and Clarke. Both of those were enormous influences for me as well. I actually corresponded with Arthur C. Clarke. We were working on an interview, but towards the end of his life, he got ill, and so we were actually setting things up, and unfortunately, his health declined, and that was. I think it was a great tragedy when he passed several years ago. But what intrigues me though is, so with the Alcubierre drive, I mean, that's kind of the official name for it. But then at the same time, I think that the media and I think that the public imagination has really picked this idea up. And this is the vision for the Star Trek warp drive, you know? And so it's interesting. You actually answered my second question, because I was going to ask, you know, did this come out of Star Trek? It sounds like that's kind of where you started. You were watching the show and you said, okay, here's this vision. How can we make this vision a reality? And so I think that the media really keyed in on that. And, you know, and again, that combined with the fact that your paper was a true hallmark. I mean, this was just a landmark paper in terms of, okay, here's how you build a warp drive, or at least here's the physics behind it, you know?
Yeah. Exactly. That was. It is true that I was watching Star Trek. People then asked me what episode I was watching. I don't remember what episode. I don't know. There was something in the Next Generation, but I can't remember the episode. But yeah, I was watching Star Trek. So the inspiration came from there, and yeah. Well, the other question you just mentioned it. People very often they ask me if I actually built or designed an engine, and of course I didn't design any kind of engine. This is just the physics behind the idea. No, I'm not an engineer. I have no idea how to design any kind of engine. It's just the physics behind the curvature of space, that you need this expansion and contraction of space. That's essentially what I did. It's actually a very short paper. The paper has only 4 pages, and it's been cited hundreds and hundreds of times by today. A lot of people that worked on different aspects of the idea. It's not terribly practical. It might actually turn out to be impossible still in practice. But at the time, nobody had actually thought about this simple model. And which was in a way surprising that nobody had thought about that in many, many decades since the beginning of general relativity.
Yeah. Well, no, that makes sense. And I think the simplicity, again, this goes to kind of that landmark aspect of it, right? Where you were able to just kind of make a statement and say, look, you know, given these parameters, this is possible within this model. Well, so one of the things I wanted to ask was, you first proposed this drive back in 1994. I mean, science has continued to advance very rapidly since the original paper was published. Do you think that it is more feasible today based on advances in physics, or do you think that it may end up going kind of a different direction?
Yeah, it's not really more feasible. People have looked at it, and it has several problems, and we haven't been able to solve those problems, even though we learned more about the problems in the last 25 years than anything else. So it has a number of problems. One problem, for example, that I always mention is the fact that I knew this from the very beginning, from the original paper I mentioned it. In order to create this geometry, as I mentioned, gravity is the distortion of space and time, is the curvature of space-time, is what we call gravity. And gravity is produced by large concentrations of mass or energy. We know that mass or energy are equivalent since E equals mc squared, right? So we usually talk about energy. So you need large concentrations of energy to produce a significant distortion or curvature in space. So I calculated the kind of energy you would need. And it came out with 2 very, very serious problems. The first one is that you actually needed something we call negative energy. And negative energy, as far as we know, doesn't actually exist. It might sound trivial, but since I mentioned energy and mass are equivalent, negative energy is equivalent to negative mass. And negative mass actually sounds really horrible. Mass is always positive, right? So we've never found anything in nature that has negative mass or negative energy. So it's not actually forbidden by the laws of physics. We don't know of any law that forbids negative energy, but we've never seen it. And all the theories, all the types of energy fields and types of matter that we know always have positive energy. Even antimatter or crazy, I don't know, all the nuclear forces, and they all have positive energy, not negative energy. So this is a serious drawback. There are small, extremely small amounts of negative energy allowed in quantum physics, something called the Casimir effect, which I even mentioned in the paper. But it allows very, very, very small concentrations of negative energy in very, very particular circumstances. So it's not clear if you can scale that to something that could be practical. That was the first problem, negative energy. The second problem that I also realized immediately was that you need huge quantities of negative energy. And you would need to turn the whole of Jupiter into negative energy to have something like a warp drive that is practical. But this is actually the best scenario. Initially, with the initial model I mentioned, people calculated that you needed about the whole energy content of the universe to create a warp bubble the size of an airplane. So it was ridiculous. But that's improved. Now you don't need a whole universe. You need something about the size of Jupiter to turn into a negative energy, to have a warp bubble moving at the speed of light that can contain something the size of an airplane, which is ridiculous, right? And how can you turn a whole planet into energy just to have one airplane move around? So the amount of negative energy is huge, and we haven't been able to reduce this significantly. So it's really hard, and even if you could, it's still negative energy, and we don't have negative energy. So it's two problems: negative energy and huge amounts of it. So those were the first two problems. There's another problem that I didn't realize immediately, but people realized eventually, and I actually saw it after a couple of years, but somebody published it before I did. So something is called the horizon problem, which means that if you're using this bubble to move faster than light, it turns out that the front of the bubble, since you're moving faster than light, if you try to send a signal from the spaceship sitting in the middle of the bubble to the front of the bubble, you can't. It will never reach it. It will get sort of stuck in the middle of the wall. So it will go a little bit further into the wall. I wouldn't be able to move forward because this signal is moving at most at the speed of light, and the bubble is moving faster than light. So you can't reach the front. And if you can't reach the front, there's a serious problem because you need to put some negative energy in the front, and you can't reach it. So how do you put the negative energy there if you can't reach it? So that's another problem. It's called the horizon problem. So because of these problems, I think it's probably not practical. I wouldn't say impossible, but maybe it will be impossible, but it's not clear at this time. But yeah, so things have gone bad. We haven't actually learned how to improve it. We've learned that it's actually difficult, and we've learned the problems. So that's one of the reasons I've never worked again on this subject. I only published the original paper in 1994, and I've never published another paper in it. Well, I did publish something about a couple of years ago with a co-author, in which both of us sort of made a summary of what people have learned over the past few years. So more than original research is more a summary what has been learned in the last 20 odd years. But that's the only second paper I published on the subject. But as I mentioned, there's hundreds of papers that other people have published on the subject in which they analyze different aspects of these problems and different aspects of the geometry and things like that.
Yeah. Well, and it's interesting. I believe, I might be mistaken, but I think Dr. Eric Davis did some papers where he tried to translate the physics that you did into string and brane theory. And that intrigued me. I think he did that back in 2006, 2007. But what intrigued me about that was, so he was taking something. I mean, it's an exciting idea to begin with, and I believe that was one of the first real papers on applied string and brane physics. So I mean, again, your work has influenced so many different things. So I guess I should also ask. It sounds like your colleagues were very supportive, and the media has had a field day with this idea. They love this idea, right? They love the Alcubierre drive. But when you first published this paper, was it well received by the scientific community in general?
Yeah, it depends. Some people were actually very happy and were enthusiastic about it, and other part of the community was not happy at all, and they thought this didn't make any sense at all. So yeah, in fact, the first journal I tried to publish the paper in rejected it and said, this is nothing interesting, and this is not interesting, and it doesn't make any sense, so we won't accept it. So I had to go to a different journal, and eventually it was published in the second journal. But this is a typical reaction. A lot of physicists, so you will find that a lot of physicists don't like science fiction. You might think it's not the case, but that's not true. There's a divided camp. So there's a lot of physicists that love science fiction, and there's a lot of physicists that hate it. And so the physicists that love science fiction tend to like the idea of the warp drive a lot, and those that hate it tend to not like the idea at all, and they always keep on saying this will never work, it doesn't make any sense. So it was well received only by a part of the community, but that part of the community has worked on the subject, and as you said, it's been influential, and the paper has been cited many times, hundreds of times, of people working on different aspects of the idea. But yeah, there's still a rejection in different parts of the scientific community that just say you should be working on something more serious, which of course I have, right? So I've only worked, as I mentioned, I only wrote the original paper back in '94 and a second sort of summary paper a couple of years ago, but that's it. All the rest of my scientific career has been on more serious subjects like black holes.
Yeah. Well, and actually, so in terms of your career, I understand that your research involves numerical relativity. So you're employing computers essentially to formulate and solve Einstein's equations at the Nuclear Sciences Institute at UNAM. Can you tell me a little bit about this research? And then does that mesh well with the Alcubierre drive, or have you really just kind of moved on into different areas?
Yeah, there are different areas. I mean, what I do is, as I mentioned, in the 90s and early 2000s, I was working on the collision of two black holes, that modeling what happens when two black holes collide and the signal of gravitational waves that we emit. This problem was extremely difficult, extremely hard to solve. The first people that tried to solve this problem on a computer were back in the 60s, early 60s, and 64 is the first paper. But they couldn't do it. It's an extremely difficult problem, not only computationally, even theoretically. It turned out to be far more complicated than people thought. And it took the community 40 years to solve the problem. I was working on this problem all of the 90s and then and the early 2000s, and it was eventually solved in 2005, not directly by me, by other groups, but colleagues, very close colleagues of mine that eventually managed to do the first simulation of the collision of two black holes that move in a spiral and eventually collide with each other and emit gravitational waves. I actually did a lot of work on that area, and many of the techniques I developed are still used today in that. I developed things about coordinate conditions and the way the equations should be written and numerical methods. So this was a community effort. It was probably about 100 people working on this subject during that time. Eventually in 2005, it was solved, and people are still doing these simulations today, but the simulation now can be done. So you just throw more computer power and more physics, complicated physics into it just to get more details. But the basic simulation can be done since about 2005. So after that, I moved on to other things, and I'm still doing numerical relativity today. But I'm studying more like gravitational collapse, which is when a black hole forms, how does it form? What happens at the moment that a black hole is being formed? What different types of fields can produce a black hole? So those are the research I've been doing in the last 15 odd years. I'm still doing that. I'm studying things that we call boson stars, which probably don't exist in nature, but they're a nice, interesting theoretical problem that you can solve with the computer. A boson star is a star that is not made of normal matter. It's made of something we call a scalar field. Something like the Higgs bosons. You probably heard about the Higgs boson. The Higgs boson is a scalar field. And if we could produce a star made of that stuff, then that would be interesting. And I'm working on that kind of problems. And it's numerical work. I actually like a lot to program. I code a lot, and when I have free time, I like to go back to my code and tweak it and see what I can do with it, because I actually relax when I'm writing computer code. It's fun. I'm fun of it. And I've been working on those sort of subjects, still numerical relativity, and which is what I've learned to do and what I really like. And these interesting things about gravitational collapse. I like also cosmology, but I've never actually done any serious work on cosmology, but I have very close colleagues that do it, so I talk to them a lot, but I've never actually worked in cosmology. And the warp drive is very different. The warp drive has nothing to do with numerical. I don't know of anyone that has actually done a numerical calculation with the warp drive. It's difficult because we don't know exactly what kind of matter would produce a warp drive. So we cannot put it in the computer to model it because we don't know what matter would do it. So it's not very closely related. But that's the sort of research I've been doing all my career. For a while, I didn't do much physics because, as you mentioned, I'm no longer am, but I was the director of the Nuclear Sciences Institute for 8 years.
Okay.
I finished that in 2020. We only get to be director of an institute in UNAM for at most 8 years. So I did the 8 years and then I moved to something else. But after that, I'm going back to these calculations of gravitational collapse, something we call critical collapse, and different types of matter fields and energy fields.
Yeah, well, and I mean, some of the things that you're getting into this is so intriguing. I mean, the Alcubierre drive itself, and you talked about this earlier, right? You get the negative energy density, and it requires some form of exotic matter or the manipulation of dark energy, right? So, I mean, again, this stuff is really getting out there towards the edge of physics. But Are there any insights? I mean, I'm not even sure if these things exist. Has there been any support for moving forward in terms of exotic matter or dark energy? Or
we well, exotic matter, we don't. It's a very generic term. It can mean anything that doesn't satisfy the usual properties of matter. So it's too generic. Dark energy is very interesting. We don't know what it is. I don't think dark energy would be good enough for a warp drive. We need something even worse than that. But dark energy is extremely interesting in cosmology. We know that there's something out there that produces an acceleration and the expansion of the universe, which is completely unexpected. Even back in the 90s, when people discovered it, they discovered it observationally with measuring the speed of the expansion of the universe, and it came as a shock. Nobody expected this. We all expected the expansion of the universe to be slowing down very slowly. We wouldn't notice it in thousands of years, but if you can actually look at very far away galaxies, you should be able to measure that it's slowing down. And it turned out that it's not slowing down, it's actually speeding up. And this was a complete shock. And we modeled it using something we call dark energy. But again, dark energy is sort of like a generic name for whatever it is that's causing the expansion to accelerate. We have some simple models. The simplest model is just to add a special constant to the equations that is actually the constant that Einstein invented back in the 20s of last century, which is the cosmological constant. You add that to the equation, it seems to work. But people don't like it because it's just an ugly constant that has a very strange value, and we don't know why it should have that. It's actually a very, very small value, an extremely small value, and it doesn't seem nice theoretically. So people invent different kinds of energy fields that could do the same work, and that's what we call dark energy. So it's an exotic kind of energy that produces a kind of anti-gravity because this accelerates the expansion of the universe, but we don't really know what it is. And I think that's one of the most exciting areas of physics, that whatever is dark energy. We have something else that we call dark matter, which is different. Dark matter is what creates the structure of the galaxies and the galaxy clusters. We don't know what it is either. So, and neither dark energy nor dark matter are part of the standard model of particle physics. It can't explain them. So if they exist, it's something else that we haven't discovered in the accelerators. We've discovered it only through cosmology. And I think that's one of the most interesting aspects of modern cosmology and modern physics. It's always more interesting when you don't really understand something, right? If you understand everything, it's nice and you can write the equations, but essentially the work is done. So it's much more interesting when you don't know something, because there's a lot of things you can try there and a lot of ideas. So yeah, but I don't think dark energy will help the world, right? Even though it is exotic matter in some way, but it's not exotic enough.
Yeah. Well, and it's interesting in terms of physics too. And this was something that intrigued me when I was reading through it. It was saying that to make the drive work, you proposed using solitary wave solutions, which are really kind of a form of soliton. And I'm a little bit familiar with that, right, in sonics. But essentially, this is kind of a wave packet that the ship would travel within. So are the solitary wave solutions, are those consistent with general relativity? And are they supported at all by quantum mechanics or recent work in string brane theory?
We don't really know. Those are good questions. So we don't really know. We don't actually have a solitary wave solution in relativity in the sense of a soliton. I mean, we have plain gravitational waves, but that's not what we're thinking. We want something more localist. And that, as far as I know, we don't actually have solutions for solitonic waves in general relativity, quantum or not. And general relativity is mostly it's a classical theory. When you want to combine it with quantum physics, it gets completely messy and nobody knows how to do it. I mean, the only solid result we have in quantum gravity, if you want, is Hawking's radiation, which is semi-classical. It's a kind of mix-up of quantum physics with gravitational classical physics, and you get that, but it's the only solid result we have. We don't actually have a good quantum theory of gravity, so we don't know if these things would be allowed in quantum gravity.
Interesting. Well, the reason I asked was, when I was reading about the solitary wave solutions, to me it reminded me a little bit of quantum wormholes, and I was wondering if there might be some similarities there or some kind of crossover, but I guess that gets super speculative. So
yeah, there's no, as far as I know, it isn't. I mean, people talk about the solitary wave solution for warp drive, but it's not. I think it's an abuse of language. It's not actually a solitary wave solution. It's a geometry that you build like you just propose this geometry, and then you figure out what sort of matter you would need. But it's not actually a solution in the sense that you're thinking about. It's not a. So I think it's just people call it like that because it looks a little bit like that, but it's not actually a solution in those sense. I actually don't like to call the warp drive a solution of the Einstein equations because it's not a solution. A solution is the other way around. When you solve the equations, you say, I have this matter, this distribution of matter, this energy field that has these properties, and then I solve to find what the geometry of space associated with it would be. And that's actually very complicated. The equations are extremely complex. What I did is the opposite way. I said, I like this geometry. What kind of matter I would need to create the geometry? And that's extremely simple to do. It just goes the other way, so it's very easy. So I don't like to call it a solution because it's not the right way to go about solutions. This is more like a designer spacetime. You like a spacetime with this geometry, and you design the geometry, and then you ask, is there any kind of matter that could do this? And that's very simple to answer. So wormholes is the same thing, right? So these are more, instead of solutions, they're designer spacetimes. They're nice geometries that you propose, and you see if there's any reasonable matter that could create them.
Yeah, yeah. Well, so one, when I was coming up with the questions, one of the things I'd wondered, I'm not sure if you've ever pondered this, and this would be kind of more engineering than it would be physics, but so in theory, we built the Alcubierre drive. We're flying through space. We're at the speed of light. Does this warp bubble? I mean, are you going to have problems with like space dust and X-rays and gamma rays and all that kind of stuff, or do you think that those would flow around this bubble?
It would depend on the form of the bubble, but people have actually looked at this. Yes, in principle, if there's something in the middle of your path, a rock or something, and you hit it, even going slower than light, it's going to be really bad if you're going very fast. So if you're going faster than light, it's going to be even worse. So yes, you would need some to design the bubbles or deflect them, but I didn't actually worry about these things when I created the original idea. Yes, you would have also any kind of light that is coming towards you, it's going to be blue shifted towards X-rays or even gamma rays probably. So it's going to be extremely dangerous for you. So you need to shield the spaceship, of course, but these are practical questions that I never went into. I just wanted to see if the geometry would allow it. Also, people have looked at, for example, if there's radiation in front of the bubble, not coming towards you, but moving away from you, you would catch up with it. So as you catch up with it, all this radiation will accumulate in the front of the bubble.
Oh.
And when you stop the bubble, all this radiation will just keep going, and it's a lot of radiation that's accumulated there. So it would be dangerous to be in front of a warp drive, even if it stops, because all the radiation will hit you. So yeah, people have looked at these things, but not myself. As I said, I was only interested in the main idea of the geometry, not so much the practical details.
Well, one of the reasons that I mentioned that, I'm kind of driving towards this idea here. So with NASA, one of the things that they've done with their robotic probe program is at least recently, they've kind of gone away from manned space flight for a number of reasons. And one of those is smaller payloads, less life support, less danger, right? I mean, they've got all the radiation issues and stuff like that. So do you think that this drive would be more practical if you scaled it down? You could avoid issues with the blue shifting, the X-rays, things like that. Do you think it would be more practical in terms of energy if it was a smaller?
Yeah, the smaller the better, and if you could produce a macroscopic warp drive, it would already be extremely exciting. Instead of sending people, if you could put a hydrogen atom in the middle just to check that if you can push something faster than light, that would be extremely exciting. And you could probably, if this turns out to be possible at all, if you could solve the problems of the negative energy and those things, you could probably test something like this in a laboratory instead of in space. You could set up a particle, the accelerator, you have a long tube, and try to move an atom through the tube or an electron faster than light. If you could create the necessary negative energy fields, that would be fantastic. And yeah, I've speculated about this, but I never wrote anything down. But yeah, I think that would be the way to do it. And then you wouldn't even have the horizon problem if you have a tube and this is going inside the tube, because you could generate the necessary fields from the outside. So yeah, that would be far more practical. And
yeah,
if you do this, then you could send packages of information faster than light, and that would revolutionize information and telecommunications even on Earth. But as I said, at this point, it probably looks not practical at all. But you
that
need
makes
negative energy. You still need negative energy, might not exist, and you would need huge quantities of it. Yes, you probably wouldn't need a planet if you're not moving a spaceship but only an atom, but you would still need ridiculous amounts of energy just to move a single atom faster than light.
Yeah. So, Miguel, let me close by asking, what comes next for you and your research? What do you hope to achieve next, and where can we look for you in the headlines?
Well, I'm not actually looking for headlines. Well, I'm trying to do much more simple things. I'm looking, as I mentioned, at gravitational collapse, critical gravitational collapse. I'm interested in cosmology, and I'm interested in, for example, in what happens inside a black hole. That's something that I'm always very interested in. We have solutions for what happens inside a black hole, but they're sort of crazy. When you look at the solution for a rotating black hole, which we've known for 50 years, we call it the Kerr solution. The interior of the black hole is completely crazy. It has wormholes that lead to other universes. It has what we call closed time-like curves, which allows you to travel back in time inside the black hole. These things make no sense at all. So that probably means that what we think, these solutions for the inside of a black hole are wrong. So I'm interested in what can happen, and for that, you can probably model collapse of some real matter and see what would happen with the real collapse and not with the solution of an eternal black hole. So things like that I'm really interested in. So I'm going to keep working on that. I have my numerical codes. I'm going to keep working for the next foreseeable future, probably on gravitational collapse and the formation of horizons and singularities. That's what it's interesting to me at this time. I might eventually go do some work in cosmology, but I'm not an expert, so I need to learn a lot about it first.
Wonderful, wonderful. Well, Miguel, thank you so much. Thank you so much for your time. It is truly an honor to be able to interview you.
You're welcome. I'm happy to be here always.
Oh, okay, and let me see. I am back. We have a bunch of blank windows too. Okay. Yeah, well, let me see. Hopefully you guys can hear me okay. I'm not sure. Yeah, I guess just let me know. Harold, are you there?
Yes, I am here. I want to ask